Hello there and welcome to Science for Sleep, where curiosity gets comfortable, big questions unfold slowly, and the universe becomes a little gentler before bedtime. Tonight, we're going to spend some time with a world that almost seems impossible. Not the largest planet ever discovered, not the hottest, not the closest, not even the strangest, though it certainly has a strong claim to that title. Instead, we're going to explore a planet so dark that it reflects almost none of the light that falls upon it. A world that circles a distant star while swallowing nearly everything that tries to illuminate it. A place so black that astronomers once struggled to explain how anything in nature could be that dark. Its name is TrES-2b. And if you've never heard of it before, don't worry, most people. After all, it's difficult to become famous for being almost impossible to see. Before we begin our journey though, I'd like to ask you something. Where in the world are you listening from tonight? Perhaps you're curled up in bed with the lights already off. Maybe you're sitting in a comfortable chair after a long day. Possibly you're listening through headphones while rain taps softly against a window somewhere. And what time is it where you are right now? A little after sunset? The middle of the night? Early morning? It's a fitting question for a story about darkness, because all of us, no matter where we happen to be, know what darkness feels like. We've all stepped into a room after the lights were turned off. We've all looked out across a countryside far from city lights and watched the stars emerge. We've all experienced those moments when our eyes slowly adjust and shapes begin to appear where moments earlier there was only blackness. Darkness is familiar, comfortable even. Yet the darkness of an TrES-2b is something entirely different. If you find this voyage soothing, interesting, or simply a pleasant way to unwind before sleep, I'd be grateful if you left a like and perhaps subscribed as well. It helps this little corner of quiet science reach others who might enjoy falling asleep while thinking about distant planets, strange discoveries, and the occasional cosmic mystery. Now then, get comfortable, allow your shoulders to relax, let the events of the day settle somewhere in the background, and together let's travel more than 700 light-years away from Earth toward a world that seems determined to disappear into the darkness around it. The story begins with a surprisingly simple question. What is the darkest thing you've ever seen? You might think of a cave, a moonless night, the bottom of the ocean, perhaps a black piece of fabric, maybe even a room with no windows and no light whatsoever. Those are all reasonable answers, yet every one of those places still reflects at least a little light. Even objects that appear completely black to our eyes are usually reflecting more light than we realize. A black t-shirt, for example, is not truly black. It simply absorbs most of the visible light that strikes it and reflects only a small amount. The same is true for black paint, black stone, black animals, black clouds, even charcoal, which many people would consider extremely dark, still reflects a measurable amount of light. Nature, it turns out, rarely produces perfect darkness. Light has a stubborn habit of bouncing around. It ricochets from surfaces, it scatters through atmospheres, it reflects from dust particles, it finds tiny paths and unexpected angles. Complete blackness is surprisingly difficult to achieve. Scientists have spent years developing special materials designed specifically to absorb as much light as possible. Some of these materials are so dark that they appear almost unsettling. When you look at them, your brain struggles to interpret what you're seeing. Shapes disappear, contours vanish. Three-dimensional objects begin to look strangely flat. It's almost as if a piece of reality has been cut away. Yet even these remarkable materials have competition. Far away among the stars, nature created something darker still. A planet. Now, when most people imagine a planet, they picture something at least vaguely familiar. Maybe blue oceans, white clouds, brown continents, or perhaps giant bands of colour like those found on Jupiter. Even distant worlds in science fiction tend to be visually dramatic. Red deserts, green forests, purple skies, sparkling ice fields. Our imaginations tend to favour colour. TrES-2b seems to have missed that memo entirely. If you could somehow travel there and observe it from nearby space, one thing would become immediately obvious. This world does not sparkle, it does not gleam, it does not shine. Instead, it absorbs almost everything. Imagine holding a lump of coal beneath bright sunlight. Now imagine something darker, then darker still. Keep going. Eventually you reach a point where ordinary comparisons stop being useful. That is roughly where TrES-2b lives, and strangely enough, this incredible darkness exists right beside intense light. Because TrES-2b doesn't drift through some cold, isolated corner of the galaxy, it orbits extremely close to its parent star. Closer than Mercury orbits our Sun. Much closer. The planet races around its star in just a little over 2 days. Think about that for a moment. While Earth requires an entire year to complete one orbit around the Sun, TrES-2b finishes the same journey in barely more than 48 hours. Its year passes faster than most weekends. The result is an environment that would feel utterly alien to us. Temperatures climb to extraordinary levels. Radiation pours down continuously. The planet is almost certainly tidally locked, meaning one side permanently faces the star while the other remains turned away. One hemisphere experiences endless daylight, the other experiences endless night, and yet neither side resembles anything we would call familiar. The world is so close to its star that darkness and heat coexist in ways that seem contradictory. We usually associate darkness with cold. After all, nighttime tends to be cooler than daytime. Shadows feel cooler than sunlight. A dark cave often feels colder than the landscape outside. Our brains naturally connect darkness with lower temperatures. TrES-2b breaks that intuition completely. This planet is dark, extraordinarily dark, yet it is also scorching hot. Imagine touching a stove burner while looking at something blacker than charcoal. That combination feels wrong somehow, and that's part of what makes this world so fascinating. It reminds us that the universe has absolutely no obligation to match our expectations. One of the most delightful aspects of astronomy is discovering how often our assumptions fail. For centuries, people believed Earth sat at the centre of everything. It didn't. People believed planets travelled in perfect circles. Mostly they don't. People imagined stars as eternal objects that never changed. They aren't. Again and again, the cosmos has demonstrated a remarkable talent for surprising us. TrES-2b continues that tradition. In fact, if someone had described this planet before it was discovered, many scientists might have been skeptical. A giant world darker than almost anything known in nature, orbiting close to a star, reflecting less than 1% of incoming light. It sounds less like astronomy and more like the setup for a science fiction novel, yet there it is, quietly circling its star, completely indifferent to our disbelief. What's particularly amusing is that astronomers found it anyway. You might think a planet that reflects almost no light would be impossible to detect. That seems reasonable. If something is extraordinarily dark, surely it should be difficult to see, and in many circumstances it would be. Yet astronomy often succeeds through indirect methods. Scientists don't necessarily need to photograph a planet directly. Instead, they watch what happens to the star. Tiny dips in brightness, subtle movements, minor changes in light. It's a little like noticing a bird flying in front of a distant street lamp. You may not see every detail of the bird itself, but you can observe the effect it has on the light. This approach has revealed thousands of planets beyond our solar system, some larger than Jupiter, some smaller than Earth, some hotter than lava, some potentially covered in oceans. Each discovery expands our understanding of what planets can be, and every now and then astronomers uncover something especially memorable, something that makes even experienced researchers pause for a moment. TrES-2b belongs in that category. Because darkness itself became the mystery. Not size, not mass, not orbit. Darkness. Imagine spending years studying distant worlds and then encountering one that appears determined to absorb nearly everything. A planet that seems less interested in reflecting starlight than swallowing it. Naturally, scientists wanted answers. Why was it so dark? What was happening inside its atmosphere? What materials existed there? Could clouds explain it? Could chemistry explain it? Could temperature explain it? Or was something even stranger taking place? Those questions would eventually lead researchers deeper into the planet's secrets. And as often happens in science, each answer produced new questions. The deeper they looked, the more unusual the world became. Meanwhile, here on Earth, darkness has always occupied a curious place in human imagination. Sometimes we fear it. Sometimes we seek it out. We build lamps to push it away. Then we travel to remote locations specifically to experience it again. Astronomers drive hours into deserts to find darker skies. Campers leave cities behind to see more stars. Entire observatories are built far from artificial light because darkness reveals things that brightness conceals. Without darkness, we wouldn't see the Milky Way stretching across the sky. Without darkness, many of the universe's most beautiful sights would remain hidden. In a strange way, darkness is not the opposite of discovery. It's often the beginning of it. The night sky itself proves that. Every evening when sunlight fades, countless distant objects become visible. Stars emerge, planets appear, galaxies reveal themselves. The universe becomes larger precisely because darkness arrives. Perhaps that's one reason stories about dark places continue to capture our imagination. Not because darkness prevents us from seeing, but because it encourages us to look more carefully. TrES-2b represents an extreme version of that idea, a world that forces astronomers to pay attention, a planet whose most remarkable feature is the apparent absence of something, light, or at least reflected light. And as we continue our journey, we'll discover that this darkness is not merely a curiosity. It's a clue pointing toward unusual atmospheric chemistry, extraordinary environmental conditions, and some of the most interesting questions scientists can ask about distant worlds. Because saying that TrES-2b is dark is only the beginning of the story. The truly fascinating part comes when we try to understand exactly what that statement means. After all, how dark is dark? What does it actually mean for a planet to reflect almost no light at all? How do astronomers measure something like that from hundreds of light years away? And perhaps most importantly, how can a world become darker than nearly anything else we know in the universe? A curious thing happens whenever astronomers describe TrES-2b. They call it a planet darker than space, and at first glance, that sounds impossible. After all, what could possibly be darker than space? If you step outside on a clear night and look upward, the sky appears black. Not dark grey, not charcoal, black. It's the benchmark we use for darkness itself. When we want to describe something extremely dark, we compare it to space. A room is dark as space. A cave is dark as space. A moonless night feels dark as space. So hearing that an actual planet might be darker than the darkness surrounding it sounds less like astronomy and more like a contradiction. Fortunately, the universe has never been particularly concerned with sounding reasonable. To understand what astronomers actually mean, we need to begin with a surprisingly simple idea. Light does not merely illuminate objects, it also reveals them. The reason you can see your hand, your pillow, your bedroom wall, or the screen you're looking at right now is because light strikes those surfaces and bounces back toward your eyes. Without reflected light, objects become difficult to see. If no light reaches your eyes at all, they disappear completely. everything around us exists in a constant exchange with light. Some surfaces reflect a great deal of it. Others absorb more than they reflect. Fresh snow, for example, reflects enormous amounts of sunlight. That's why snowy landscapes can appear dazzlingly bright. In fact, snow can reflect more than 80% of incoming sunlight. That's an extraordinary amount. If sunlight were money, snow would be returning most of it immediately. A black asphalt road behaves very differently. Instead of reflecting most incoming light, it absorbs much of it. That's one reason roads become so hot during summer afternoons. The energy doesn't bounce away, it stays. Every object occupies some position along this spectrum. Some are bright, some are dark, some fall somewhere in between. Scientists have a specific term for measuring this property. They call it albedo. Albedo is simply the fraction of incoming light that an object reflects. The concept sounds technical, but it's actually very straightforward. Imagine 100 particles of light arriving at a surface. If 90 of them bounce away, the object has high albedo. If only 10 escape while the rest are absorbed, the object has a low albedo. It's basically a scorecard for reflectivity. Earth has an average albedo of about 30%. That means our planet reflects roughly 1/3 of the sunlight that reaches it. Clouds contribute significantly to that brightness. Ice caps help as well. Viewed from space, Earth appears surprisingly reflective. Venus is even brighter. Its thick cloud layers reflect enormous amounts of sunlight. Venus reflects roughly 75% of incoming light. If planets participated in brightness competitions, Venus would be showing off constantly. The Moon, by contrast, is darker than many people realize. Because it appears bright in the night sky, people often assume it must be highly reflective. In reality, the Moon reflects only about 12% of incoming sunlight. Fresh asphalt can actually be darker. The Moon merely appears brilliant because it's illuminated by the sun against a dark background. Perspective changes everything. Then we arrive at TrES-2b, and the numbers suddenly become astonishing. Measurements suggest that TrES-2b reflects less than 1% of the light that strikes it. Less than 1%. Pause for a moment and consider how extraordinary that is. Imagine receiving $100 and returning less than a single dollar. That's roughly what the planet does with starlight. Nearly everything stays, almost nothing leaves. The planet absorbs the overwhelming majority of the energy that reaches it. This is why headlines often described it as darker than coal, darker than black paint, darker than most naturally occurring materials on Earth. Those comparisons were not exaggerations. They were attempts to help people grasp just how unusual the measurements were. But now we encounter another question. If TrES-2b reflects so little light, why compare it to space? Why not simply say it's extremely dark? The answer lies in something subtle. Outer space isn't actually an object, it's mostly emptiness. When we look into space, we're not usually seeing a giant black surface. We're seeing the absence of matter. The darkness comes from the fact that there is very little nearby material available to reflect sunlight toward us. Yet space isn't completely black. Far from it. Stars shine, dust scatters light, gas clouds glow, galaxies radiate energy. Even seemingly empty regions contain particles, radiation, and faint illumination. Astronomers can detect all sorts of signals coming from areas that appear completely dark to human eyes. The universe is surprisingly busy. Now imagine placing an object against that backdrop. Normally, the object would reflect enough light to stand out. A planet illuminated by a nearby star should be visible, because some portion of the incoming light bounces back into space. Most planets behave this way. Jupiter reflects quite a bit. Saturn reflects a fair amount. Even distant Neptune appears bright because its atmosphere scatters sunlight effectively. TrES-2b barely participates in this process. Instead of reflecting starlight, it absorbs it. As a result, the the contrast between the planet and surrounding space becomes unusually small. In certain observations, the world appears almost like a hole cut into reality. Not because it's literally darker than nothingness, but because it contributes so little reflected light of its own. It's a subtle distinction. The phrase darker than space isn't a strict physical statement, it's a visual one, a descriptive shortcut, a way of communicating just how astonishingly little light escapes from the planet. Human language occasionally struggles when confronting extreme astronomy. This is one of those moments. After all, our everyday experiences rarely prepare us for a world that reflects less than 1% of incoming starlight. We simply don't encounter objects like that very often. Even shadows aren't truly black. A shadow outdoors still contains scattered light from the sky, moonlight, reflections from nearby surfaces. Photographers know this well. What appears dark to our eyes often contains surprising amounts of illumination. Nature loves subtle light. TrES-2b seems determined to reject it, and that's what makes it so fascinating. Interestingly, darkness itself can be deceptive. Our brains are not particularly good at judging absolute brightness. Instead, we rely on comparisons. A candle appears bright in a dark room. The same candle becomes almost invisible beneath direct sunlight. The candle hasn't changed, only the context has. Astronomers face similar challenges. Brightness is often measured relative to surrounding objects. A planet may appear bright compared to one star and dim compared to another. Context matters enormously. When researchers studied TrES-2b, they weren't simply looking at photographs and saying, "That looks dark." They were making careful measurements, observing tiny changes in brightness, calculating how much light should be reflected, comparing observations with theoretical models. The process resembles detective work more than sightseeing. Imagine hearing a faint sound behind a wall. You don't see the source directly. Instead, you gather clues, volume, timing, echoes, patterns. Eventually, you reconstruct what's happening. Exoplanet astronomy works much the same way. Scientists rarely observe these distant worlds directly. Instead, they infer their properties from subtle effects. A slight dimming of starlight, a tiny gravitational tug, a faint change in brightness. From those clues emerges an entire planetary portrait. It's one of the most impressive achievements in modern science. We've become remarkably good at studying places we cannot visit. Places so distant that light itself requires hundreds of years to reach us. And yet, from those faint signals, researchers concluded that TrES-2b was among the darkest planets ever discovered. Naturally, this raised another question. What happens to all the light it absorbs? Energy doesn't simply vanish. The universe tends to keep track of such things. If sunlight, or rather starlight, isn't reflected away, it must go somewhere. The answer is heat, an enormous amount of heat. Every photon absorbed by the atmosphere contributes energy. Over time, that energy accumulates. The planet warms, temperatures climb, and this leads to one of the strangest aspects of TrES-2b. Its darkness does not indicate coldness. Quite the opposite. The world is incredibly hot. This feels counterintuitive because our everyday experiences teach us different lessons. Darkness often arrives with nighttime. Nighttime often brings cooler temperatures. The two become linked in our minds. But on TrES-2b, darkness and heat coexist. The planet absorbs light so efficiently that it becomes hotter as a result. It's almost like a cosmic solar collector, except instead of gathering sunlight for useful purposes, it simply bakes beneath the relentless energy of its nearby star. The relationship between brightness and temperature appears throughout astronomy. Stars themselves demonstrate it. Some stars shine brilliantly because they generate immense amounts of energy. Planets, meanwhile, often reveal their temperatures through the light they emit. A sufficiently hot object glows. Metal removed from a furnace glows. Lava glows. Stars glow. TrES-2b exists in an intriguing middle ground. It reflects almost no visible light, yet it still emits thermal radiation because it is hot. In other words, the planet isn't completely invisible, it merely hides in a different way. If our eyes were sensitive to infrared radiation instead of visible light, the universe would look dramatically different. People would glow, buildings would glow, animals would glow, and TrES-2b would glow as well. Just not in the wavelengths human eyes normally perceive. This distinction is important because it reminds us that darkness depends partly on the observer. Human vision covers only a tiny fraction of the electromagnetic spectrum. Visible light occupies a narrow range. Outside that range lies a vast universe of signals: infrared, ultraviolet, radio waves, X-rays, gamma rays. The cosmos is overflowing with information our eyes never detect. Astronomers compensate by building instruments capable of observing these invisible wavelengths. Thanks to those instruments, apparently dark worlds often reveal unexpected secrets. A planet that appears black in visible light may be blazing in infrared. A dark cloud may glow brightly in radio frequencies. Reality is richer than our senses alone suggest. TrES-2b provides a perfect example. Its extraordinary darkness tells only part of the story. The deeper question becomes why? Why does the atmosphere absorb so much light? What chemicals are responsible? What conditions allow such extreme darkness to exist? Because planets don't simply decide to become black. Physical processes create those outcomes. Chemistry matters, temperature matters, atmospheric structure matters. Some combination of factors transform TrES-2b into one of the least reflective worlds ever observed. Long before TrES-2b became famous for being one of the darkest worlds ever discovered, it was simply another faint signal hidden among thousands of stars. No dramatic announcement accompanied its first appearance. No telescope captured a breathtaking image of a black planet drifting through space. Nobody looked through an eyepiece and suddenly gasped, "There it is." The discovery happened in a much quieter way. A tiny dip in starlight. A subtle change in brightness. A pattern so small that most people would never notice it. And yet that tiny signal would eventually reveal an entire world. One of the most remarkable aspects of modern astronomy is that planets are often discovered without being seen directly. That may sound strange at first. After all, if you want to discover a mountain, you look at the mountain. If you want to discover an island, you find the island. If you want to discover a new species of bird, you observe the bird. Planets around distant stars present a different challenge. They're usually overwhelmed by the light of their parent stars. Imagine trying to spot a firefly hovering beside a searchlight from thousands of kilometers away. The searchlight dominates everything. The firefly becomes almost impossible to see. That is roughly the situation astronomers face when searching for exoplanets. The stars are bright, the planets are not, and the distances involved are difficult to comprehend. TrES-2b resides approximately 750 light-years from Earth. The light reaching us tonight left that system centuries ago. Back when people on Earth were using telescopes far less sophisticated than the ones we have today, photons were already beginning their journey across interstellar space. By the time those photons arrived, entire generations had come and gone. That distance alone makes planetary discovery extraordinarily difficult. Yet astronomers have become remarkably skilled at finding worlds hidden within the glare of distant stars. The story of TrES-2b begins during a period when exoplanet discoveries were accelerating rapidly. For most of human history, planets beyond our solar system existed only as speculation. People wondered whether other stars possessed their own planetary families. The idea seemed reasonable. After all, our sun had planets. Why wouldn't other stars? But wondering and knowing are very different things. For centuries nobody had proof. The night sky remained full of possibilities but short on answers. Then, during the late 20th century, everything changed. improved instruments, better detectors, more powerful computers, new observational techniques. One by one, astronomers began discovering worlds orbiting distant stars. At first, each discovery felt extraordinary. Today, thousands of exoplanets are known. Yet during the early years, every new detection represented something historic. Each planet expanded humanity's understanding of the universe. Each discovery answered a question that had persisted for generations. Are planets common? The answer appeared to be yes, very common, perhaps astonishingly common. Among those efforts was a project called the Transatlantic Exoplanet Survey. Astronomers often enjoy creating memorable acronyms, and this one became known simply as TrES. The project involved a network of relatively small telescopes working together to search for planets around distant stars. That detail surprises many people. When people imagine planetary discoveries, they often picture enormous observatories perched atop remote mountains. Sometimes those facilities play critical roles, but TrES demonstrated that smaller instruments could accomplish remarkable things as well. The telescopes used in the survey were modest by professional astronomy standards. Nothing like the giant observatories that dominate astronomy magazines. Instead, they relied on patience, precision, and repetition. Night after night, they monitored thousands of stars, watching, measuring, recording, searching for tiny changes in brightness. The technique they employed is called the transit method, and it remains one of the most successful planet hunting tools ever developed. The concept is surprisingly elegant. Imagine looking at a distant lamp. Now imagine a small object passing directly between you and the lamp. For a brief moment, the lamp appears slightly dimmer. Not much, just a little. If the object passes in front of the lamp repeatedly, a pattern emerges. Brightness drops, brightness returns. Then the cycle repeats. Astronomers search for exactly this behavior among stars. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of starlight. The star becomes slightly dimmer. Then it brightens again after the planet moves on. If this dimming occurs regularly, scientists have strong evidence that a planet is present. It's a wonderfully clever method. Rather than looking directly for the planet, researchers watch the star. The planet reveals itself indirectly, like footprints revealing an unseen traveller, or ripples revealing a fish beneath the water. The planet's existence becomes apparent through its effects. This approach requires astonishing precision. Stars do not dim very much during planetary transits. In many cases, brightness changes by less than 1%. Imagine trying to detect the difference between 99 light bulbs and 100 light bulbs from a great distance. That's the level of sensitivity involved, yet modern instruments can accomplish exactly that. During the survey, astronomers noticed one particular star displaying an intriguing pattern. Its brightness dropped slightly, then recovered, then dropped again and again. The timing was consistent. The signal repeated reliably. That consistency immediately attracted attention. Random fluctuations happen all the time. Stars can vary naturally. Instruments produce noise. Observations contain imperfections. But repeating patterns are different. Repeating patterns suggest causes, and one possible cause was a planet. Further observations followed. Scientists gathered more data. They checked calculations. They examined alternative explanations. Astronomy is careful work. Nobody wants to announce a planet only to discover later that a detector malfunctioned or a different phenomenon was responsible. Evidence accumulates gradually. Confidence builds slowly. Eventually, the conclusion became difficult to avoid. A planet was orbiting that distant star. The discovery was officially announced in 2006. The world received the designation TrES-2b. The naming convention sounds a bit technical, but astronomers often prioritize practicality over poetry. The star itself became known as TrES-2. The planet received the letter B because it was the first planet discovered around that star. Simple, efficient, perhaps not particularly romantic, but functional. At the time, the discovery was interesting for several reasons. The planet belonged to a category known as hot Jupiters. These are giant gas planets similar in size to Jupiter, but orbiting extremely close to their stars. When hot Jupiters were first discovered, they surprised astronomers enormously. Our own solar system contains nothing quite like them. Jupiter resides far from the Sun, cold by comparison, stable, comfortably distant. Hot Jupiters do the opposite. They crowd their stars. They endure extreme radiation. Their years last only days. Their existence forced scientists to rethink planetary formation theories. TrES-2b fit this unusual category. It possessed roughly the size of Jupiter. Its mass was substantial, and it orbited astonishingly close to its star. A year there lasted barely more than 2 Earth days. Imagine celebrating your birthday every 48 hours. You'd accumulate centuries of birthdays before reaching retirement age. The planet completed orbits with remarkable speed. At first, that alone made TrES-2b worthy of scientific attention. But the truly unusual discovery came later, because finding the planet was only the beginning. Once astronomers knew it existed, they wanted to learn more. How massive was it? How hot was it? What was its atmosphere like? What chemicals were present? Could they measure reflected light? These questions required increasingly sophisticated observations. Fortunately, astronomy was entering a new era. A particularly important contributor arrived in 2009, NASA's Kepler Space Telescope. Kepler was designed specifically to search for exoplanets using the transit method. Positioned above Earth's atmosphere, it could observe stars with extraordinary precision. Freed from atmospheric distortions, it detected subtle brightness changes impossible to measure from the ground alone. Its observations transformed exoplanet science. Thousands of planetary candidates emerged. Entire catalogues of new worlds appeared. And among the planets Kepler studied was TrES-2b. Researchers began examining the system in greater detail than ever before. What they discovered was astonishing. Remember, planets reveal themselves not only during transits, but also throughout their orbits. As a planet circles its star, different amounts of reflected light reach observers. A bright planet contributes measurable illumination. A dark planet contributes very little. By analysing tiny brightness changes throughout the orbit, scientists can estimate reflectivity. Essentially, they ask a simple question. How much starlight bounces off the planet and returns toward us? For most planets, some measurable amount exists. Perhaps a lot, perhaps a little, but something, but... TrES-2b delivered an unexpected answer. Almost nothing. The measurement suggested reflectivity so low that astronomers initially struggled to comprehend it. The planet appeared far darker than expected, far darker than Jupiter, far darker than Earth, far darker than most objects familiar to everyday experience. Imagine attending a competition to determine the darkest object in a room. You bring charcoal, someone else brings black velvet, another participant brings black paint. Then TrES-2b arrives and quietly wins by an absurd margin. That's roughly what the data implied. This was not merely a dark planet. This was a world operating near the limits of planetary darkness. Naturally, scientists became fascinated. Discoveries often become memorable when they challenge expectations. TrES-2b certainly accomplished that. Finding a giant planet wasn't shocking. By then, many hot Jupiters had already been discovered. Finding an extraordinarily dark giant planet was different. That result demanded explanation. Why would a world absorb so much light? What atmospheric conditions could create such behaviour? What chemical processes were occurring high above the planet's cloud tops? These questions transformed TrES-2b from an ordinary exoplanet into a scientific mystery. And the mystery only deepened as researchers gathered more information. One particularly intriguing aspect involved the star itself. The host star resembles our Sun in several ways. It's not an exotic monster star, not a red giant, not a neutron star, not something dramatically unusual. Instead, it's relatively ordinary, which made the planet's behaviour even more interesting. Extreme planets around extreme stars can sometimes be explained easily, but TrES-2b existed within a system that appeared comparatively normal. The star wasn't the primary mystery. The planet was. As additional observations accumulated, astronomers gradually assembled a more complete picture. They estimated temperatures, refined orbital parameters, studied atmospheric properties. Each new piece of information contributed to a growing understanding of the world. Yet one feature consistently stood out: darkness. Again and again, measurements pointed toward the same conclusion. The planet reflected remarkably little light. It's difficult to overstate how surprising this was. Nature usually offers some degree of reflectivity. Clouds scatter light. Atmospheres scatter light. Particles scatter light. Even dark surfaces tend to return at least modest amounts of illumination. TrES-2b seemed unusually committed to doing the opposite. The more researchers investigated, the more they realized that this wasn't a simple observational curiosity. Something physically significant was occurring within the atmosphere itself. Something was allowing incoming starlight to vanish with extraordinary efficiency. And that realization shifted scientific attention toward a deeper question, not how the planet was discovered. That part had already been solved. The more intriguing challenge was understanding the mechanism behind the darkness. What atmospheric ingredients were responsible? How could a gas giant become darker than nearly every planet known? What processes were operating beneath the relentless heat of its nearby star? Consider for a moment just how difficult it is to make something truly black. Not dark, not grey, not charcoal-coloured, truly black. The kind of blackness that seems to absorb attention itself. Humans have spent centuries trying to create darker and darker materials. Artists experimented with pigments. Manufacturers developed special coatings. Scientists engineered sophisticated surfaces designed to trap incoming light. And yet even our darkest material still reflects some portion of the illumination that reaches them. Light is persistent. It bounces, scatters, escapes. Finding ways to eliminate those reflections completely turns out to be remarkably challenging. Nature faces the same challenge. Most planets reflect at least some light. Clouds reflect light. Ice reflects light. Atmospheric particles reflect light. Even worlds that appear relatively dark usually send a measurable amount of starlight back into space. TrES-2b seems determined to do the opposite. It behaves almost like a cosmic trap for photons. Light arrives, and then, for the most part, it stays. This naturally raises the question that puzzled astronomers after the planet's extraordinary darkness was confirmed. Why? What makes this particular world so incredibly dark? Why does it absorb nearly everything instead of reflecting it? The answer turns out to involve a combination of temperature, chemistry, atmospheric structure, and some surprisingly unusual conditions that don't exist on the planets most of us know best. And like many mysteries in astronomy, the explanation begins with a reminder that TrES-2b is not Earth. It's not even remotely Earth-like. Sometimes when people hear the word planet, their minds automatically drift toward familiar images. Clouds, weather, skies, perhaps oceans or mountains, maybe deserts, perhaps forests if imagination gets involved. The word planet feels familiar because we live on one, yet the overwhelming majority of planets discovered beyond our solar system are profoundly alien. TrES-2b belongs firmly in that category. This is a giant gas planet, roughly similar in size to Jupiter. But unlike Jupiter, it lives extraordinarily close to its star. The distance is so small that the entire environment operates according to different rules. Imagine taking Jupiter and dragging it inward until it sat closer to the Sun than Mercury. The result would be catastrophic. Temperatures would soar, atmospheric chemistry would change, cloud structures would transform, the entire planet would become something new. That's essentially what happened with TrES-2b. The world receives enormous amounts of stellar radiation. Its atmosphere endures relentless heating day after day, year after year. Except, of course, a year there lasts barely more than 2 Earth days. Everything happens quickly. The planet races around its star at tremendous speed. And because it likely became tidally locked long ago, one hemisphere continuously faces the star. The same side receives the punishment endlessly. No sunrise, no sunset, just constant exposure. The significance of this heat cannot be overstated. Temperature influences chemistry. Chemistry influences clouds. Clouds influence reflectivity. And reflectivity determines how bright a planet appears. These factors become deeply connected. Here on Earth, clouds play a major role in making our world bright. When sunlight strikes a thick white cloud, much of that light scatters in different directions. Some returns to space, some reaches observers. Clouds are excellent reflectors. They contribute significantly to Earth's overall brightness. Venus provides an even more dramatic example. Its dense cloud layers reflect huge amounts of sunlight. That's why Venus appears so brilliant in the night sky. Its atmosphere behaves almost like a giant mirror. If TrES-2b possessed similar cloud structures, it would likely appear much brighter. But conditions there prevent that from happening. The temperatures are simply too extreme. Many of the compounds that form reflective clouds elsewhere cannot survive comfortably in such an environment. The atmospheric ingredients behave differently. Cloud formation changes. Reflective layers become less effective. As a result, incoming light encounters fewer opportunities to bounce back into space. Instead, it penetrates deeper into the atmosphere, and once it enters, another process begins. Absorption. Imagine sunlight entering a dense forest. Some light reaches the ground, some strikes leaves, some bounces between branches. The deeper the light travels, the greater the chance that something eventually absorbs it. A similar principle operates within planetary atmospheres. Photons enter. They interact with molecules. Some scatter away. Others disappear into the atmospheric structure itself. On TrES-2b, absorption seems extraordinarily efficient. The atmosphere behaves less like a mirror and more like a sponge. Light arrives. The sponge soaks it up. Very little escapes. Researchers believe several atmospheric ingredients may contribute to this behavior. One possibility involves gaseous sodium and potassium. These elements exist in many planetary atmospheres. Under the extreme conditions present on TrES-2b, they may remain suspended as gases rather than condensing into other forms. Both sodium and potassium are capable of absorbing visible light. That characteristic makes them particularly interesting. Instead of reflecting incoming illumination, they help remove it. It's a bit like covering windows with dark curtains. The light enters but finds fewer opportunities to leave. Astronomers have also considered the role of titanium oxide and vanadium oxide. These substances are not exactly common household conversation topics. Few people sit down at dinner and discuss vanadium oxide. Yet in the atmospheres of hot exoplanets, such compounds can become important. Under extremely high temperatures, they may exist as gases. These molecules interact strongly with incoming radiation. They absorb energy efficiently, and when enough absorbing compounds accumulate, planetary brightness decreases. The atmosphere essentially becomes a giant energy collector. Photons enter, energy remains, reflection drops, darkness increases. One useful way to think about this process is to imagine clothing on a hot summer day. Suppose you wear a white shirt. Much sunlight reflects away. the fabric remains relatively cooler. Now imagine wearing black clothing. More sunlight is absorbed, temperatures rise, the material becomes warmer. TrES-2b behaves somewhat like an enormous planetary version of that black shirt, except the effect operates on a vastly larger scale. The atmosphere continually absorbs energy instead of reflecting it. As a result, the world remains both dark and extremely hot. This combination helps explain one of the planet's most surprising features. Its darkness isn't caused by a lack of light. Quite the opposite. The planet receives tremendous amounts of starlight. The problem is that very little returns. Imagine standing beside an enormous spotlight while wearing clothing that absorbs nearly every photon striking it. You would be brightly illuminated from the spotlight's perspective, yet appear remarkably dark to distant observers. That's roughly what's happening here. The star is not weak. The illumination is not scarce. The atmosphere simply refuses to give much of it back. Interestingly, some of the darkest materials ever created on Earth operate according to a similar principle. Scientists have engineered substances containing microscopic structures that trap incoming light. Photons enter these tiny forests of tubes or fibers. They bounce around repeatedly. Each bounce increases the chance of absorption. Eventually, almost all the light disappears. The material becomes extraordinarily black. When people first see such materials, they often describe them as unnatural. Three-dimensional objects appear strangely flat. Details vanish. The brain becomes confused because it expects at least some reflected light to reveal shapes and contours. Without those reflections, visual information begins to disappear. TrES-2b achieves something conceptually similar through atmospheric processes rather than engineered nanostructures. No scientist built this world. Nature did. And somehow, nature produced an atmosphere capable of rivaling some of the darkest materials humans have ever developed. That's a remarkable accomplishment for a planet, especially one located hundreds of light years away. Another important factor involves what the atmosphere may lack. Sometimes scientific explanations focus on what exists. Other times they focus on what's missing. Reflective clouds are one example. On cooler worlds, cloud particles can scatter large amounts of light. These clouds brighten planetary appearances dramatically. On TrES-2b, extreme temperatures may prevent the formation of certain highly reflective cloud types. Without those bright cloud layers, the atmosphere loses an important source of reflectivity. Imagine removing mirrors from a room. The room immediately becomes darker. Not because additional darkness was added, simply because fewer surfaces remain available to reflect light. The same principle applies here. Less reflection naturally means more absorption. More absorption naturally means greater darkness. Scientists continue studying these processes because exoplanet atmospheres are extraordinarily complex. No single factor explains everything. Temperature matters, pressure matters, chemical composition matters, wind patterns matter, cloud formation matters, radiation matters. These ingredients interact continuously. Changing one can influence all the others. Planetary atmospheres are less like simple machines and more like dynamic ecosystems. Everything affects everything else. TrES-2b happens to occupy a particularly extreme corner of that spectrum. Its conditions push atmospheric behavior toward unusual outcomes. Darkness becomes one of those outcomes. And yet there is something almost ironic about the entire situation. The planet became famous because it appears black. But the blackness itself is actually evidence of intense activity. The atmosphere isn't inactive, it's not empty. It's not dead. Quite the opposite. The darkness exists because complex physical processes are occurring continuously. Molecules absorb energy. Heat moves through atmospheric layers. Winds transport material. Radiation interacts with gases. The atmosphere remains busy every moment. Its darkness is a consequence of that activity, not an absence of it. This is one of the recurring lessons astronomy teaches us. Appearances can be deceptive. A quiet-looking object may conceal extraordinary processes. A faint signal may reveal a giant planet. A dark world may be blisteringly hot. The universe often rewards closer inspection. TrES-2b certainly does. Because once scientists understood that the darkness was real, they began investigating how incoming starlight behaved after entering the atmosphere. Where exactly did the energy go? How was it transported? What happened to the absorbed radiation? Let's imagine something for a moment. You're standing beneath an enormous spotlight. The beam is so bright that it overwhelms everything around you. Light pours down continuously, second after second, hour after hour. Now imagine that instead of reflecting that light, your clothing somehow absorbs almost all of it. Very little bounces away, very little escapes. The energy arrives and simply stays. From a distance, observers might struggle to see you clearly, despite the incredible brightness shining directly upon you. In a simplified way, this is what TrES-2b does every day of its existence. The planet sits extraordinarily close to its star. Starlight crashes into its atmosphere continuously. An immense flood of energy arrives every second. Yet almost none of that visible light is reflected back into space. Instead, the atmosphere behaves like a giant trap, a cosmic absorber, a world that seems remarkably efficient at swallowing incoming illumination. And once scientists began examining this process more closely, they realized that TrES-2b isn't merely dark. It is actively consuming vast amounts of stellar energy. That distinction matters. Darkness alone sounds passive. A black object sitting quietly in space, a shadow, an absence, something empty. But TrES-2b is anything but passive. Its atmosphere is busy, dynamic, violent, constantly interacting with the radiation pouring down from its nearby star. The darkness is not evidence of inactivity. It is evidence of absorption, an astonishing amount of absorption. To appreciate how extreme this situation is, it helps to consider the scale of the planet's orbit. Earth sits approximately 150 million kilometers from the Sun. That distance may sound enormous, and it is. Yet, TrES-2b circles its star at only a fraction of that separation. The planet hugs its star so closely that an entire orbit takes just over 2 Earth days. Imagine watching a planet complete a year before a long weekend has ended. That's the environment we're dealing with. The star dominates the sky. Its radiation dominates the atmosphere. Its influence dominates everything. On Earth, sunlight feels pleasant on a cool morning. On TrES-2b, the experience would be entirely different. The planet receives a relentless bombardment of energy, not a gentle warming, not a comfortable glow, a continuous assault. And because so little of that energy is reflected away, much of it remains trapped within the atmosphere. The result is a world that becomes extraordinarily hot. This relationship between absorption and temperature appears throughout nature. Consider a parked car during summer. A white car often remains cooler than a black one. Why? Because the white surface reflects more sunlight. The black surface absorbs more. The energy stays. Temperatures rise. The principle is straightforward. Reflect less. Absorb more. Heat up. TrES-2b takes this idea to an extreme rarely seen in planetary science. The atmosphere behaves almost like a gigantic heat collector. Every incoming photon becomes an opportunity for absorption. Every absorbed photon contributes energy. And over time, that energy builds into something extraordinary. Astronomers estimate temperatures on the day side of the planet can exceed 1,000 degrees Celsius. Some estimates push even higher depending on atmospheric conditions. Pause for a moment and imagine what that means. Water cannot survive as liquid. Many familiar materials would melt. Lead would soften. Tin would liquefy. Entire environments we consider normal simply cease to exist. and yet despite these temperatures the planet remains remarkably dark. That combination continues to surprise people. Our intuition expects bright things to be hot. Fire glows. Molten metal glows. Stars glow. Brightness and heat often travel together. TrES-2b challenges that assumption. It remains dark because it reflects very little visible light, but internally the atmosphere is processing enormous quantities of energy. It's a bit like a stove burner hidden beneath a black cloth. The heat remains very real even if the brightness appears subdued. One of the most fascinating aspects of this process involves what happens after starlight enters the atmosphere. The photons do not simply vanish. Energy must go somewhere. Physics is stubborn about that. Whenever light is absorbed, its energy becomes part of the system. In this case, the atmosphere gains energy. Molecules begin moving faster, temperatures rise, winds develop, heat starts flowing from one region to another. The atmosphere becomes a vast engine powered by absorbed starlight. Imagine an ocean constantly receiving heat from below. Currents would form, temperatures would vary, energy would move from hotter regions toward cooler ones. Something similar occurs on TrES-2b. The day side receives enormous amounts of stellar energy. The night side receives none directly. This creates dramatic temperature differences across the planet. Nature generally dislikes imbalances. Whenever one area becomes hotter than another, energy begins moving. Air flows, winds accelerate, heat attempts to redistribute itself. Researchers believe winds on hot Jupiters can reach astonishing speeds, thousands of kilometers per hour in some cases, faster than the most powerful hurricanes on Earth, far faster. The atmosphere effectively becomes a giant conveyor belt attempting to transport heat away from the intensely illuminated hemisphere. Imagine weather systems operating on a planetary scale with energy levels far beyond anything our world experiences. That's the kind of environment likely present on TrES-2b, and all of it begins with absorbed starlight. The darkness itself fuels the process. The more efficiently the atmosphere absorbs radiation, the more energy becomes available to drive atmospheric motion. In a strange way, the planet's darkness powers its weather. That idea feels almost backwards. We often associate darkness with inactivity, quiet, stillness. Yet here darkness becomes evidence of extraordinary activity. The atmosphere is not sleeping. It is working continuously, moving energy, redistributing heat, responding to the constant flood of radiation from the nearby star. Another intriguing consequence involves the planet's appearance. Suppose you could somehow travel to the TrES-2 system and observe the world from nearby space. What would you actually see? At first glance, perhaps not much. The planet would appear surprisingly difficult to distinguish. Not because it lacks size. TrES-2b is enormous, larger than Earth by a tremendous margin. Instead, the challenge comes from reflectivity. Most planets announce themselves by bouncing light toward observers. TrES-2b largely refuses. Imagine placing a lump of extremely black material against a dark background. Its outline becomes difficult to perceive, details disappear, contrast decreases. The object seems strangely unreal. The planet likely produces a similar impression, not invisible, but elusive, almost ghost-like despite its immense size. There is something wonderfully ironic about that. A giant world hiding in plain sight. A planet large enough to swallow Earth many times over, yet visually reluctant to reveal itself. Astronomy is full of these contradictions. The biggest objects are not always the easiest to see. The brightest environments can produce the darkest worlds. The universe seems to enjoy challenging expectations. Scientists investigating TrES-2b soon realized that understanding the darkness required understanding the atmosphere itself. The atmosphere wasn't merely a container surrounding the planet, it was the key. Everything pointed back to atmospheric behavior. What gases existed there? How were they distributed? How did they interact with incoming radiation? Which molecules absorb the most energy? How deep did starlight penetrate before being captured? These questions became increasingly important, because once light enters an atmosphere, its journey can become surprisingly complicated. Some photons bounce away immediately, others scatter multiple times, some penetrate deeper layers, still others are absorbed by specific molecules. Each possibility affects what astronomers ultimately observe. Imagine sunlight entering a dense forest. Some rays reach the ground directly. Others strike leaves. Others bounce between branches before disappearing. The final outcome depends on countless interactions. Planetary atmospheres behave similarly, except instead of trees and leaves, the actors are gases, molecules, particles, and temperature gradients. TrES-2b appears to possess atmospheric conditions uniquely suited for absorption. The atmosphere acts less like a mirror and more like a maze. Light enters. The chances of escape become increasingly small. Eventually, most of it ends up converted into heat. Researchers sometimes compare planetary atmospheres to filters. Some atmospheres allow certain wavelengths to pass through easily. Others block them. Some reflect strongly. Others absorb strongly. TrES-2b seems particularly effective at the absorbing part. It's as though nature built a filter specifically designed to capture visible light. And while the exact details remain subjects of ongoing study, the overall picture is remarkably consistent. Incoming starlight arrives. The atmosphere captures most of it. The planet heats up. Atmospheric circulation responds. Energy spreads across the globe. The cycle repeats endlessly. Day after day. Year after 2-day year. For millions or perhaps billions of years. This continuous process transforms TrES-2b into something unusual, even among hot Jupiters. Many planets orbit close to their stars. Many experience extreme temperatures. Few combine such intense heating with such extraordinary darkness. That's what makes this world memorable. It's not merely hot, it's not merely dark, it's both simultaneously. And those two characteristics are connected. The darkness helps create the heat. The heat influences the atmosphere. The atmosphere sustains the darkness. Everything becomes part of the same system. One feature supports another. Another supports the next. The result is a self-consistent planetary environment unlike anything in our own solar system. Perhaps that's why TrES-2b continues attracting scientific attention years after its discovery. The planet offers a natural laboratory, a place where astronomers can study atmospheric physics under extreme conditions, a world that pushes familiar processes into unfamiliar territory. Every observation helps researchers understand not only this particular planet, but also countless others. Because if one atmosphere can become this effective at absorbing light, what other atmospheric possibilities might exist elsewhere? The universe contains hundreds of billions of stars in our galaxy alone. Most likely many possess planets. Some may be brighter than anything we have imagined. Others may be darker still. Each discovery expands the menu of planetary possibilities, and TrES-2b occupies one of the most fascinating entries on that menu. A giant world that sits beside a brilliant star while consuming nearly all the light that reaches it. A planet that transforms incoming illumination into heat, wind, and atmospheric motion. A world that doesn't merely receive starlight, it swallows it. Most of us have a fairly comfortable relationship with the sun. We complain when it's too hot. We enjoy it when it's pleasantly warm. We wear sunglasses on bright afternoons and search for shade during summer. Yet despite occasional heat waves and sunburns, Earth exists at a remarkably safe distance from its star. The sun dominates our solar system, but it doesn't overwhelm our daily lives. There's enough sunlight for oceans, forests, weather systems, and life itself, while still leaving room for cool evenings and changing seasons. In many ways, Earth occupies a fortunate middle ground. Not too close, not too far. TrES-2b was not granted that luxury. The planet lives in a very different neighbourhood. If Earth's relationship with the Sun resembles living across town from a powerful industrial furnace, then TrES-2b is practically renting an apartment beside it. Its star fills the sky. Its radiation dominates everything. Its influence reaches into every corner of the atmosphere. Nothing escapes it. And once we begin examining just how close this planet actually is to its star, the darkness of TrES-2b starts to make even more sense. Distance matters enormously in astronomy. A small change in distance can produce dramatic consequences. Imagine sitting beside a campfire. A few steps away feels comfortable. Move closer and the warmth increases. Closer still and it becomes uncomfortable. Continue moving forward and eventually the heat becomes unbearable. The fire itself hasn't changed. Only your distance has. Stars operate according to the same principle. The closer a planet moves toward its star, the more energy it receives. That increase happens surprisingly quickly. Double your distance from a star and the incoming energy drops dramatically. Cut the distance in half and the energy rises enormously. Nature is not subtle about this. The universe rewards proximity with heat. Lots of heat. TrES-2b circles its parent star at a distance of only a few million kilometers. That may sound large from a human perspective, but on astronomical scales it is astonishingly close. Mercury, the innermost planet in our solar system, would appear almost cautious by comparison. The orbit of TrES-2b is so tight that the entire planet completes a journey around its star in approximately 2.47 Earth days. To put that into perspective, by the time you finish a typical work week, TrES-2b would have celebrated multiple New Years. Its calendar is absurdly short. Its seasons, if they existed at all, would be meaningless. Everything about the planet's existence revolves around proximity. Close to the star, close to the radiation, close to the heat, close to the source of the energy that shapes every aspect of its atmosphere. The host star itself is often described as somewhat similar to our Sun. This makes the situation even more interesting. We're not dealing with some monstrous blue giant hundreds of times brighter than our star. We're not dealing with an exotic stellar object behaving in unusual ways. Instead, the star is relatively ordinary. It's the orbit that is extraordinary. Take a reasonably familiar star and place a giant planet almost on top of it. Suddenly, everything changes. Astronomers classify TrES-2b as a hot Jupiter for precisely this reason. Hot Jupiters are giant gas planets occupying locations where giant planets probably shouldn't exist, according to older theories of planetary formation. For a long time, scientists assumed Jupiter-like planets formed far from their stars. That idea made sense. In our own solar system, Jupiter, Saturn, Uranus and Neptune all reside in the colder outer regions. The pattern seemed logical. Large gas giants formed where temperatures were lower and abundant material existed. Then, exoplanet discoveries arrived and cheerfully disrupted those assumptions. Astronomers began finding giant planets in places nobody expected. Worlds larger than Jupiter orbiting closer than Mercury. Some completing orbits in only a few days, others in even less time. The universe once again demonstrated that it wasn't obligated to follow human expectations. TrES-2b belongs to this strange family. And because it does, the planet experiences conditions that have no direct equivalent in our solar system. One consequence becomes apparent almost immediately. The atmosphere receives staggering amounts of radiation. Every second, enormous quantities of energy arrive from the nearby star. Visible light, infrared radiation, ultraviolet energy, a continuous torrent of stellar output pours into the atmosphere. Earth receives sunlight and converts part of that energy into weather. TrES-2b receives far more. The result is weather on an entirely different scale. Of course, Calling it weather may not fully capture what's happening. When people hear the word weather, they imagine rain, clouds, wind, maybe snow if they're unlucky. TrES-2b likely experiences atmospheric behaviour so extreme that familiar weather terms begin to feel inadequate. The atmosphere is heated relentlessly. Temperatures climb beyond what most terrestrial environments could tolerate. Powerful winds emerge. Energy flows continuously from hotter regions toward cooler ones. Everything operates under conditions that would appear completely alien to human experience. Another important consequence of the planet's orbit involves tidal locking. Scientists strongly suspect that TrES-2b is tidally locked to its star. This means the same side always faces the star while the opposite side always faces away. Many people are familiar with this concept because our moon behaves similarly toward Earth. We always see the same lunar face. The far side remains hidden from direct view. TrES-2b likely experiences the same phenomenon on a planetary scale. One hemisphere lives beneath perpetual daylight. The other exists beneath perpetual darkness. No sunrise, no sunset, no dawn, no twilight, no changing skies. The star hangs permanently overhead on one side of the planet. On the other side, it never appears at all. That arrangement creates some fascinating consequences. Imagine living somewhere where noon never ends, hour after hour, day after day, year after year. The star remains fixed in the sky. Its radiation never weakens. Its heat never leaves. There are no cool nights to provide relief. No evening breezes signaling the end of the day. The atmosphere must continuously cope with incoming energy. Now imagine the opposite hemisphere. A place where direct starlight never arrives. No sunrise ever breaks the horizon. No morning follows the night. Darkness remains permanent. At first glance, you might expect that side of the planet to be extremely cold. The reality is more complicated. Remember all the absorbed energy we discussed earlier. The atmosphere does not simply allow heat to remain trapped on the day side forever. Air moves. Energy moves. Winds transport warmth across the globe. The planet essentially tries to balance itself, not perfectly, but continuously. Researchers studying hot Jupiters believe that atmospheric circulation can become incredibly powerful. Heat absorbed on the illuminated hemisphere gets carried toward the darker hemisphere through global wind systems. Some estimates suggest wind speeds reaching several thousand kilometers per hour. That is difficult to visualize. The strongest hurricanes on Earth would seem modest by comparison. Imagine standing in weather driven by energy differences spanning an entire planet. Fortunately, no one is likely to visit TrES-2b anytime soon, because those winds are only part of the challenge. Temperature remains the dominant factor. Scientists estimate that the day side of the planet reaches temperatures exceeding 1000 degrees Celsius. Some models suggest even higher values depending on atmospheric conditions. These are temperatures capable of altering chemistry itself. Substances that exist as solids on Earth may become liquids or gases. Materials familiar to us behave differently. The atmospheric environment enters territory that simply doesn't exist naturally on our planet. Interestingly, this extreme heat helps explain some of the world's unusual darkness. Earlier, we discussed how reflective clouds contribute to planetary brightness. Earth has clouds, Venus has clouds, Jupiter has clouds. Clouds often increase reflectivity significantly. But under the temperatures found on TrES-2b, atmospheric chemistry changes dramatically. Certain cloud-forming materials may struggle to survive. Other compounds remain gaseous. The atmosphere becomes less reflective and more absorptive. In a sense, the star helps create the darkness. Its relentless heating shapes the atmospheric conditions responsible for absorbing so much incoming light. The relationship becomes cyclical. The planet absorbs starlight efficiently. Absorption increases heat. Heat changes atmospheric behavior. Atmospheric behavior maintains low reflectivity. Low reflectivity allows even more absorption. The entire system reinforces itself. This is one reason astronomers find hot Jupiters so fascinating. These worlds push familiar physics into unfamiliar territory. The same basic processes operate everywhere: radiation, atmospheric chemistry, heat transfer, fluid dynamics. Yet under extreme conditions, those processes produce outcomes that seem almost impossible. A giant black planet orbiting beside a blazing star feels like one of those outcomes, something nature shouldn't allow. And yet, there it is, orbit after orbit, year after 2-day year, continuing exactly as physics predicts. Another remarkable feature involves the appearance of the star itself from the planet's perspective. If you could somehow stand above the atmosphere on the permanently illuminated hemisphere, the star would dominate the sky. It would appear vastly larger than our Sun appears from Earth. Not because the star itself is larger, but because the distance is so much smaller. The visual effect would be dramatic. The star would command attention constantly. There would be no escaping it, no turning away, no waiting for sunset. The source of the planet's energy would remain permanently visible. That's one reason the title of this section feels so appropriate. TrES-2b truly lives beside a relentless sun, not necessarily because the star is unusual, not because the star is malicious. Stars don't possess intentions, they simply shine. The relentlessness comes from the orbit. The planet never gets a break, never gains distance, never experiences seasonal relief, never drifts temporarily into a cooler environment. The star remains close, the radiation remains intense, the heating remains continuous. For billions of years that relationship may have persisted. Imagine the cumulative effect. Billions of years spent orbiting near the same star. Billions of years absorbing energy. Billions of years experiencing atmospheric conditions shaped by that proximity. Over such timescales, entire planetary identities emerge. Earth became a world of oceans, weather, and life. Jupiter became a giant storm-filled gas planet. TrES-2b became something else. A dark world, a hot world, a world defined largely by its relationship with its star. Yet this raises another question. If the planet absorbs so much energy, and if temperatures climb so high as a result, what would life actually be like there? What kind of environment emerges when darkness and extreme heat coexist on the same world? At first glance, the phrase sounds almost self-contradictory. The hottest darkness in the universe. Most of us instinctively separate those two ideas. Heat belongs with brightness. Darkness belongs with coolness. A blazing campfire lights the night. Molten metal glows orange. Stars shine because they are hot. Even a simple electric stove burner begins glowing red once temperatures become high enough. Throughout our lives, heat and light seem to travel together. One usually announces the other. That expectation is so deeply rooted in everyday experience that TrES-2b feels almost impossible when you first encounter it. How can a planet be both extraordinarily dark and extraordinarily hot? Shouldn't all that heat produce brightness? Shouldn't a world receiving such intense stellar radiation reflect more light? Shouldn't something be glowing brilliantly? The answer, as is often the case in astronomy, depends on understanding exactly what kind of light we're talking about. Human beings experience only a tiny slice of reality. That isn't a criticism, it's simply biology. Our eyes evolved under conditions found on Earth. The visible spectrum, the rainbow of colours from red to violet, is the range our vision can detect. Everything outside that range remains invisible to us without technological assistance. Yet the universe is filled with forms of light beyond human sight. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, gamma rays. They're all part of the same electromagnetic family. Our eyes just happen to notice a very small portion of it. This becomes important when discussing TrES-2b. because the planet is dark in visible light. That's the crucial detail. It reflects very little of the starlight our eyes would normally see, but that doesn't mean the planet is inactive, and it certainly doesn't mean the planet is cold. In fact, the absorbed energy has to go somewhere, and that energy transforms the atmosphere into one of the hottest environments ever studied among exoplanets. Imagine leaving a black metal object under direct sunlight all day. The object absorbs radiation, its temperature rises. Hours later, it may become almost too hot to touch. The same principle operates on TrES-2b, but on a planetary scale. The atmosphere captures incoming energy with extraordinary efficiency. Over time, temperatures climb to astonishing levels. Researchers estimate atmospheric temperatures reaching well above 1,000 degrees Celsius. Some regions may exceed 1,700 degrees Celsius, depending on location and atmospheric conditions. Numbers like that can feel abstract. After all, very few people regularly encounter temperatures measured in thousands of degrees, so it helps to compare them with familiar examples. At around 1,500 degrees Celsius, many metals begin melting. Lava commonly ranges between 700 and 1,200 degrees Celsius depending on composition. Industrial furnaces operate within similar ranges. The day side of TrES-2b exists comfortably within this territory. This is not a warm world, not a hot world. It's a world where heat becomes one of the defining characteristics of existence itself. And yet, if you somehow observed it using ordinary human vision, it would still appear astonishingly dark. That contrast is what makes the planet so memorable. The darkness isn't caused by a lack of energy. It's caused by a lack of reflected visible light. Those are very different things. A useful comparison might involve a cast iron skillet. Imagine placing a black skillet onto a stove. At first it looks ordinary. As it absorbs heat, its temperature rises dramatically, yet for a long time it doesn't visibly glow. The heat becomes intense long before your eyes detect significant brightness. The skillet contains energy. Lots of energy. It's just not radiating most of that energy in wavelengths your eyes easily perceive. Something similar occurs on TrES-2b. The atmosphere absorbs enormous quantities of stellar radiation. The energy remains, the temperatures rise, but the visible reflection remains extraordinarily low. Consequently, the world appears dark even while behaving thermally like an enormous furnace. This distinction helps explain why astronomers often describe the planet as black rather than cold. Blackness and coldness are not the same thing. A black object absorbs energy efficiently. A cold object simply contains less thermal energy. Sometimes those characteristics occur together, sometimes they do not. TrES-2b demonstrates the difference beautifully. It's one of the darkest known planets, and simultaneously one of the hottest. The atmosphere effectively turns absorbed starlight into heat, and because so little visible light escapes, the planet maintains its reputation as an unusually dark world. There's another fascinating consequence of these temperatures. The atmosphere itself begins behaving differently than atmospheres on cooler planets. Chemistry changes, molecules break apart, different compounds become stable, others disappear entirely. Conditions that would be impossible on Earth become routine. Imagine trying to predict weather on a world where atmospheric temperatures exceed those found inside many industrial processes. Our everyday experience offers very little guidance. Clouds, for example, become a particularly interesting topic. When most people think of clouds, they imagine water droplets, white formations drifting across blue skies, perhaps dark rain clouds before a storm. But clouds can be made from many different materials. On other planets, entirely unfamiliar substances can condense and form cloud layers. Scientists studying hot exoplanets have proposed clouds composed of materials that sound more appropriate for geology textbooks than weather reports: silicates, metal compounds, exotic condensates. The universe is wonderfully creative when temperatures become extreme. TrES-2b occupies a regime where ordinary expectations about cloud formation begin breaking down. Some reflective cloud materials may struggle to form, others may exist only temporarily. The atmosphere becomes a difficult place for brightness to survive, and because cloud properties influence planetary reflectivity, these conditions likely contribute to the planet's remarkable darkness. Heat and darkness become linked through atmospheric chemistry. The star provides energy. The atmosphere absorbs that energy. The resulting temperatures alter atmospheric behavior. Atmospheric behavior sustains the darkness. Everything becomes interconnected. One process reinforces another. Astronomers often describe planets as systems rather than objects. TrES-2b demonstrates why. The darkness isn't an isolated feature. The heat isn't an isolated feature. The atmosphere isn't an isolated feature. Each depends on the others. Remove one component and the entire planetary character changes. This interconnectedness becomes especially apparent when researchers attempt to model the atmosphere. Computer simulations must account for countless variables: temperature gradients, radiation transport, chemical reactions, wind patterns, pressure differences, heat circulation. Every factor influences the rest. Planetary atmospheres are astonishingly complex. Even Earth's atmosphere remains difficult to predict perfectly, despite centuries of study and an abundance of observations. Now imagine trying to model a giant gas planet hundreds of light years away. A world with temperatures exceeding 1,000 degrees. A world receiving relentless stellar radiation. A world darker than almost any other known planet. The challenge becomes and yet scientists continue refining their understanding year after year. Each new observation adds another piece to the puzzle. One particularly intriguing aspect involves how the planet emits energy. Remember, absorbed energy cannot remain trapped forever. Eventually it must leave. The atmosphere continually radiates energy back into space. But much of that radiation emerges at infrared wavelengths rather than visible ones. This means the planet effectively glows in forms of light our eyes cannot detect. If human vision extended into the infrared, TrES-2b would look very different. The darkness would largely disappear. Instead, observers might see a world radiating thermal energy intensely. In other words, the planet isn't truly invisible. It's merely hiding from the specific range of wavelengths human eyes happen to use. That realization offers an important reminder about astronomy. The universe often appears strange because our senses are limited. Many discoveries become understandable once we expand beyond ordinary perception. Radio telescopes reveal structures invisible to optical telescopes. Infrared observatories detect heat hidden from human vision. X-ray instruments uncover violent cosmic events occurring across the universe. Every wavelength tells a different story. TrES-2b's story depends heavily on that principle. Visible light portrays it as a nearly black world. Infrared observations reveal a much hotter and more active reality. Both descriptions are correct. Neither tells the whole story alone. Another remarkable feature of the planet's environment involves the enormous amount of energy flowing through the atmosphere. Imagine an engine running continuously, not for hours, not for days, for millions or billions of years. The atmosphere receives energy from the star, processes that energy, moves it around the globe, radiates part of it back into space, then repeats the cycle endlessly. This constant circulation likely drives powerful atmospheric dynamics. Researchers studying hot Jupiters often find evidence for heat transport on a global scale. The atmosphere attempts to redistribute absorbed energy from hotter regions toward cooler regions. Enormous winds emerge. Temperature differences shape circulation patterns. Entire hemispheres become linked through atmospheric motion. The planet essentially operates as a giant heat engine, and all of it originates from its close relationship with the star. Without that proximity, TrES-2b would become a completely different world. move it outward, and temperatures would fall. Chemistry would change, cloud structures might change, reflectivity could increase dramatically, the darkness itself might weaken. The planet's identity depends heavily on where it lives. Location determines everything. It's a reminder that planets are shaped not only by what they are, but also by where they are. Earth's position helped create oceans and life. Jupiter's position helped create a cold giant atmosphere. TrES-2b's position helped create one of the hottest dark worlds ever discovered. Perhaps the most astonishing aspect of all this is how counterintuitive it remains. Even after hearing the explanation, many people still instinctively connect darkness with coldness. The association is powerful, understandably so. Our everyday experiences reinforce it constantly. Yet the universe rarely limits itself to human intuition. Again and again, astronomy reveals environments that seem impossible until physics explains them. TrES-2b belongs firmly in that category. A giant world, blazing temperatures, a nearly black appearance, an atmosphere that absorbs extraordinary amounts of stellar energy. The combination sounds almost fictional, yet the measurements support it. The models support it. The observations support it. Nature created a world where darkness and heat coexist in spectacular fashion. And perhaps the strangest part is that despite all this discussion of temperatures, chemistry and atmospheric physics, we still haven't answered a very natural question. What would the planet actually look like? Suppose an observer could travel safely to the system and view TrES-2b from nearby space. Not through scientific instruments, not through graphs or data. Simply with their own eyes. Would they see a black sphere, a glowing world, a faint outline against the stars, something else entirely? Imagine that technology has advanced far beyond anything available today. Space travel has become routine. Distances measured in hundreds of light years no longer seem intimidating. The journey to the TrES-2 system takes days instead of centuries, and after a long voyage through interstellar darkness, your spacecraft finally arrives. Ahead of you hangs the star, bright, steady, familiar in some ways, unfamiliar in others, and somewhere nearby is the destination you've travelled so far to see, one of the darkest worlds ever discovered. Naturally, your eyes search for it immediately, and that's where the first surprise occurs. You don't see it, at least not right away. Most planets announce their presence. Jupiter practically demands attention. Saturn's rings stretch across space like a cosmic advertisement. Even distant Neptune shines with a beautiful blue colour. Planets tend to reveal themselves willingly. TrES-2b does not. The star dominates your view. Its light spills across nearby space. Your instruments confirm that the planet is exactly where it should be. Yet visually, it remains elusive, almost hidden. Imagine looking for a black cat inside a dark room. Now imagine the cat is the size of Jupiter and the room is outer space. That begins to capture the challenge. Eventually, your eyes adjust. Your instruments help. And slowly, a shape emerges. Not bright, not colourful, not dramatic. A silhouette, a giant absence. A sphere that seems less like an object and more like a missing piece of reality. The first impression would probably be unsettling. Human vision relies heavily on reflected light. Reflections reveal shape. Reflections reveal texture. Reflections reveal distance. Take those reflections away, and the brain begins struggling to interpret what it's seeing. This effect occurs on Earth with some of the darkest materials ever created. Scientists have developed coatings so black that three-dimensional objects appear strangely flat. A crumpled surface looks smooth. A sculpture looks two-dimensional. The usual visual clues disappear. People often describe the experience as slightly disturbing because the brain expects information that never arrives. Now imagine applying that effect to an entire planet. A world larger than Jupiter. a world suspended against a backdrop of stars, a world reflecting almost none of the visible light falling upon it. The result would be extraordinary. The planet would appear less like a globe and more like a hole cut into the universe. Of course, it wouldn't literally be invisible. Nothing that large could truly disappear. The outline would remain. The star behind it would vanish where the planet blocked the light. Its shape would gradually become apparent. But compared with other planets, the visual impression would be remarkably subdued. The darkness itself would become the defining feature. What's particularly fascinating is that our solar system offers nothing quite like it. We have dark places, very dark places. Yet even the darkest locations in our cosmic neighbourhood struggle to compete with TrES-2b. Let's start with the Moon. People often imagine the Moon as bright because it dominates the night sky. In reality, the lunar surface is surprisingly dark. Fresh snow reflects vastly more sunlight than the Moon does. If the Moon were somehow placed beside a snowy field under identical lighting conditions, the snow would appear dramatically brighter. The Moon's average reflectivity is only about 12%. That might sound low, and it is. Yet TrES-2b reflects far less. The Moon practically glows by comparison. Then there is Mercury. The innermost planet of our solar system receives intense sunlight and possesses a relatively dark surface. Its rocky terrain absorbs significant amounts of incoming radiation. Mercury reflects only a modest fraction of sunlight. Even so, it appears bright compared with TrES-2b. A world reflecting less than 1% of incoming light exists in an entirely different category. Next, we can consider the dark regions found on various moons. Saturn's moon Iapetus contains one of the most striking examples. One hemisphere is dramatically darker than the other. The contrast is so extreme that the moon resembles a cosmic yin-yang symbol. Astronomers spent years trying to understand the phenomenon. The dark hemisphere absorbs far more sunlight than the brighter regions, yet even those famously dark terrains remain substantially more reflective than TrES-2b. The planet continues winning every darkness competition, and it isn't particularly close. Perhaps the best solar system comparison comes from comets. Certain comet nuclei rank among the darkest natural objects known. These icy bodies accumulate layers of dark, carbon-rich material over time. Their surfaces absorb sunlight efficiently. Some reflect only a few % of incoming light. When measured against ordinary planetary standards, they appear remarkably black. For a while, comet nuclei held the reputation as some of the darkest objects astronomers routinely observed. Then TrES-2b entered the conversation. Suddenly those comets seemed almost reflective. That's a remarkable achievement. When a planet begins outperforming comet nuclei in a darkness contest, you've entered unusual territory. Another fascinating comparison involves the oceans of Earth. Many people assume deep water appears black because light struggles to penetrate it. Indeed, portions of the open ocean can look incredibly dark under certain conditions. Looking down into deep water sometimes creates the impression of staring into an abyss. Yet even oceans reflect sunlight. Waves scatter light. The surface glitters. Sunsets create dazzling reflections. Viewed from space, Earth remains bright compared with TrES-2b. The oceans contribute beauty. The atmosphere contributes brightness. Clouds contribute even more. Our planet and TrES-2b almost occupy opposite ends of the reflectivity spectrum. One world shines, the other swallows. And that brings us back to the view from orbit. Suppose your spacecraft moves closer. The planet gradually fills more of the window. Details begin emerging, not because reflected light suddenly increases, but because your perspective improves. The immense scale becomes apparent. This is not a small object, not a lonely asteroid drifting through darkness. This is a giant gas planet, a world large enough to dwarf Earth, a world whose atmosphere extends across enormous distances, and yet the darkness remains. The planet seems determined to absorb attention rather than reflect it. You might notice something else as well. The darkness is not perfectly uniform. Real atmospheres are complicated. Winds move material. Temperatures vary. Chemistry changes from place to place. Subtle differences would likely emerge under close observation. The planet wouldn't resemble a featureless black billiard ball. Instead, it would possess atmospheric structures, though many might be difficult to see in visible light. Remember, the atmosphere remains active. Powerful winds transport energy. Heat circulates continuously. The planet is alive with motion despite its visual silence. In some ways, that's one of the most intriguing aspects of TrES-2b. The appearance suggests stillness. The reality suggests activity. The darkness creates an illusion of calm. The atmosphere tells a different story. Gigantic weather systems likely rage across the globe. Heat moves between hemispheres. Chemical reactions unfold constantly. The planet remains busy every second. It simply hides much of that activity behind a curtain of darkness. There's another subtle detail worth imagining: the stars. Ordinary planets often appear against the star field as brightly illuminated objects. TrES-2b would likely create a different impression. The surrounding stars might seem unusually prominent because the planet contributes so little visible light of its own. The contrast could produce a surprisingly dramatic scene. A giant dark sphere floating among countless points of light. The stars shine, the planet absorbs, two opposite approaches to interacting with energy sharing the same view. Astronomers often talk about exoplanets as data. Graphs, measurements, light curves, spectra. Those tools are essential. Without them, worlds like TrES-2b would remain undiscovered. Yet occasionally it's useful to pause and visualize what those numbers represent. Because behind every measurement lies an actual place, a real world, not fictional, not hypothetical, an actual planet orbiting an actual star hundreds of light years away. Somewhere right now, as you're listening to this story, TrES-2b continues racing around its star, completing another orbit, absorbing more radiation, maintaining its remarkable darkness. The planet doesn't know it's famous. It doesn't know astronomers study it. It simply exists, a giant black world following the laws of physics. Perhaps that's what makes astronomy so captivating. Every discovery reminds us that reality is larger than imagination alone. Before exoplanets were discovered, worlds like TrES-2b belonged almost entirely to speculation. Now they belong to science. The universe revealed something stranger than many people would have invented. A planet darker than nearly anything known. A giant world orbiting beside a blazing star. A place where heat and darkness coexist. And despite all of that, TrES-2b may not even be the strangest world waiting to be found. Thousands of exoplanets have already been discovered. Thousands more likely remain hidden in existing data. Millions probably await future detection. Every year brings surprises. Every new telescope expands the search. Every improved instrument reveals previously invisible details, which means TrES-2b is not merely a destination, it's a clue. A reminder that planetary diversity is far greater than we once believed. Some worlds shine brilliantly. Others hide within darkness. Some reflect starlight like mirrors. Others consume it almost completely. And once astronomers realized just how unusual TrES-2b appeared compared with anything in our own solar system, attention naturally shifted toward another intriguing question. If TrES-2b absorbs nearly all the light that reaches it, and if it reflects less than 1% of incoming starlight, why isn't it completely invisible? After all, that seems like the logical conclusion. A planet that reflects almost nothing should simply disappear. It should vanish into the darkness around it. Astronomers shouldn't be able to detect it. Telescopes shouldn't be able to study it. And yet they can. Not only did scientists discover TrES-2b, but they've also measured its orbit, estimated its temperature, studied aspects of its atmosphere, and calculated just how dark it really is. Clearly something is reaching us. Some signal is escaping. Some information continues making the long journey across hundreds of light years of space. The answer turns out to reveal one of the most fascinating lessons in astronomy. Darkness and invisibility are not the same thing. In everyday life, we often treat them as if they are. When something becomes difficult to see, we call it dark. When a room loses its lighting, we say it becomes invisible. The two ideas feel connected, yet physics treats them very differently. Darkness concerns reflected light. Invisibility concerns detection, and detection can happen in many ways. A black cat in a dark room might be difficult to see, but if it meows, moves, or brushes against your leg, you immediately know it's there. The cat never became invisible. It merely stopped reflecting enough light for easy visual identification. Astronomers use a similar approach when studying distant worlds. They don't rely exclusively on direct images. In fact, most exoplanets have never been photographed in the traditional sense. Instead, scientists detect them through their effects, their influence, their interactions with stars, their signatures hidden within light. TrES-2b remains a perfect example. Long before astronomers understood how dark the planet was, they already knew it existed. The planet announced itself through motion, through timing, through changes in starlight. Every time it passed in front of its star, a tiny portion of the star's brightness disappeared. Then the brightness returned, then the cycle repeated, again and again and again. A pattern emerged. The pattern told a story. Something was crossing the face of the star, something large, something orbiting, something planetary. The darkness of TrES-2b never prevented that discovery because the planet wasn't being found through reflected light. It was being found through blocked light. Those are very different things. Imagine holding a black coin in front of a flashlight. The coin may be extremely dark, it may reflect almost nothing, yet the shadow it creates remains obvious. In fact, the darker the coin, the more complete the shadow becomes. Astronomers often work with similar principles. Sometimes the absence of light reveals more than the presence of it. This idea appears throughout astronomy. Black holes, for example, emit no light directly. Yet scientists detect them regularly, not because they shine, but because they influence nearby stars, gas and radiation. Dark objects leave fingerprints. Their existence shapes the environment around them. TrES-2b does exactly that. The planet leaves evidence everywhere. Its orbit affects observations. Its atmosphere influences measurements. Its passage changes stellar brightness. Its heat produces radiation. Its existence becomes impossible to ignore, even though the planet itself reflects very little visible light. This distinction becomes even more interesting when we think about what black actually means. Many people imagine blackness as a complete absence of light. Physics takes a more nuanced view. A black object is usually an object that absorbs most incoming light. Notice the wording, most, not all. That's an important difference. Nature rarely deals in absolutes. Even the darkest known materials reflect tiny amounts of light. The blackest laboratory coatings ever created still allow minute fractions of light to escape. A small percentage remains visible. TrES-2b behaves similarly. The planet absorbs the overwhelming majority of incoming starlight, yet not every photon becomes trapped. Some light still escapes, very small amounts, but enough for sensitive instruments to measure. Imagine standing in a vast concert hall while someone whispers from the opposite end. Your ears might fail completely. You'd hear nothing. Replace your ears with a sophisticated microphone, however, and suddenly the whisper becomes detectable. Astronomical instruments function in much the same way. They possess sensitivity far beyond human perception. Signals that seem invisible to us become measurable to modern telescopes. Tiny brightness differences become valuable information. Minute fluctuations become scientific discoveries. This is one reason astronomy often feels almost magical. The universe appears silent and empty to our senses. Then instruments reveal an astonishing amount of activity. Everywhere, at every scale. The same principle applies to TrES-2b. Human eyes would struggle. Scientific instruments excel. Another important reason the planet isn't invisible involves heat. Earlier we discussed how TrES-2b absorbs enormous amounts of stellar energy. That energy doesn't simply remain trapped forever. Eventually it must leave. Physics insists upon balance. If energy enters continuously, energy must also escape continuously. Otherwise temperatures would rise forever. The atmosphere solves this problem by radiating energy back into space, not primarily as visible light, but as infrared radiation. This is where the story becomes especially interesting. Suppose human eyes evolved differently. Suppose instead of seeing visible light, we saw infrared radiation. The universe would look profoundly different. People would glow, animals would glow, buildings would glow, fresh footprints might remain visible for hours, coffee cups would shine after being filled with hot drinks, and TrES-2b would no longer appear especially dark. It would look like a giant source of thermal radiation, because that's exactly what it is. The planet continuously emits heat. The darkness exists only within a particular range of wavelengths. Visible light. Outside that range, a different picture emerges. This realization highlights something important about astronomy. Every observation depends partly on how you choose to observe. Look in visible light and one story appears. Look in infrared and another story emerges. Neither story is wrong. They're simply different perspectives on the same reality. Astronomers routinely exploit this fact. Modern telescopes examine the universe across multiple wavelengths. Visible light reveals one set of details. Infrared reveals another. Radio waves reveal another. X-rays reveal another. The cosmos transforms depending on how it's viewed. TrES-2b teaches this lesson beautifully. Visible observations emphasize darkness. Infrared observations emphasize heat. Together they create a more complete understanding. There's another subtle reason the planet remains detectable: contrast. Human vision depends heavily on contrast. Astronomical observations do as well. A dark object against a bright background often becomes easier to detect than people expect. Consider a solar eclipse. The moon appears dark because it blocks sunlight, yet the moon becomes impossible to ignore. Its darkness actually enhances its visibility. The contrast creates a dramatic effect. TrES-2b benefits from similar principles during certain observations. The star provides a bright reference point. The planet modifies the system's brightness slightly. Scientists measure those modifications with extraordinary precision. The planet's darkness doesn't eliminate the signal. It changes the nature of the signal, and because astronomers understand that signal, they can extract information from it. One of the most remarkable achievements in exoplanet science involves this ability to infer enormous amounts of information from tiny changes in light. Imagine standing on a distant hill and watching a house through a small window. You never enter the building. You never see the occupants directly. Yet over time you notice patterns. Lights switch on, lights switch off, shadows move, doors open, doors close. Eventually you begin understanding what's happening inside. Astronomers do something similar with planets. They rarely observe the worlds directly. Instead, they observe effects, patterns, signatures, changes, and from those clues, entire planetary portraits emerge. This process allowed scientists to estimate the reflectivity of TrES-2b. The planet itself remained distant. The measurements remained subtle, yet the conclusions became increasingly clear. The world reflected astonishingly little light, not zero, but very close. close enough to earn its reputation as one of the darkest planets ever discovered, close enough to inspire headlines around the world, close enough to challenge assumptions about what planets can be. Another fascinating aspect involves the idea of perfect darkness itself. People often speak about perfect blackness as though it exists somewhere in nature. The reality is more complicated. Perfect absorbers are theoretical ideals. Scientists call them black bodies. A perfect black body absorbs all incoming radiation. None escapes through reflection. Everything is captured. Real objects only approximate this behavior. Some come closer than others. TrES-2b happens to come unusually close compared with most planets. But it doesn't reach perfection. A tiny amount of reflection remains. A tiny amount of visible light survives. Nature allows enough information to escape for astronomers to study the world, and we're fortunate that it does. Because if the planet truly reflected nothing and emitted nothing detectable, understanding it would become vastly more difficult. The universe often reveals itself through imperfections, a slight reflection, a faint glow, a tiny fluctuation. These subtle clues make discovery possible. In many ways, astronomy depends on them. Another thought experiment may help illustrate the idea. Imagine standing in a completely dark theatre. On the stage sits a black object. At first you see nothing. Then someone turns on the faintest possible spotlight. Suddenly an outline appears. Not much, just enough. The object remains mostly hidden, but its existence becomes undeniable. TrES-2b occupies a similar position. The planet never becomes brilliantly illuminated. The signal remains faint, yet it is sufficient. Modern instruments can detect what human senses would miss entirely. And because of that capability, astronomers transformed a nearly invisible world into one of the most famous exoplanets ever discovered. The irony is delightful. A planet celebrated for being difficult to see. A world known precisely because it reflects almost no light. A giant sphere of darkness becoming scientifically famous. The universe occasionally possesses a sense of humour. Perhaps that's why TrES-2b remains so memorable, not merely because it is dark, but because it demonstrates how science works. Discovery isn't always about looking directly at something. Sometimes it's about noticing consequences, measuring effects, following clues, extracting meaning from subtle signals, and once astronomers learned how to read those signals, they uncovered a world unlike anything in our solar system. Yet TrES-2b is far from alone in the universe. Thousands of exoplanets have already been discovered. Some are hotter, some are colder, some are brighter, some are stranger. Many challenge our assumptions in completely different ways, which naturally leads us toward a broader question. If one planet can become nearly black while another reflects enormous amounts of light, what other extremes exist among the worlds beyond our solar system? Not very long ago, astronomers faced a very different problem. They weren't trying to understand why one planet was darker than another. They weren't comparing atmospheric chemistry. They weren't debating reflectivity measurements. They weren't building catalogues filled with exotic worlds. They were simply hoping to find a single planet beyond our solar system. Just one. That goal alone seemed ambitious. For most of human history, planets orbiting other stars belonged more to philosophy than science. People suspected they existed. Many thought they probably did. The night sky contains hundreds of billions of stars, and it seemed unlikely that our sun would be the only one surrounded by planets. Yet suspicion isn't evidence. Astronomy required proof, then the proof arrived. And after the first discoveries, something remarkable happened. The universe began revealing just how creative it could be. One by one, planets appeared that nobody had predicted. Worlds unlike anything in our own solar system. Planets orbiting impossibly close to stars. Planets larger than Jupiter. Planets smaller than Earth. Planets with temperatures hot enough to melt rock. Planets that might possess global oceans. planets with multiple suns in their skies. Every few years, another discovery arrived that forced scientists to expand their understanding of what a planet could be. TrES-2b belongs to that tradition. Its extraordinary darkness challenged expectations. But once astronomers started comparing it with other exoplanets, they discovered something equally fascinating. The universe doesn't just produce dark worlds, it produces every imaginable variation of light and shadow. Some planets swallow starlight. Others seem determined to reflect as much of it as possible. Some glow. Some shimmer. Some appear almost mirror-like, and together they form a collection of environments far stranger than most science fiction writers would have dared invent a century ago. To appreciate just how unusual TrES-2b is, it helps to place it within this broader family of strange worlds. Let's begin with one of the most famous examples, a planet called Kepler-7b. If TrES-2b is the champion of darkness, Kepler-7b occupies almost the opposite end of the spectrum. The world possesses unusually reflective cloud layers that scatter large amounts of incoming starlight. Observations suggest bright cloud formations covering portions of its atmosphere. Instead of absorbing most of the energy that arrives, parts of the atmosphere behave more like giant reflectors. Imagine two neighbouring worlds. One absorbs nearly everything, the other sends significant amounts of light back into space. Both planets exist because the same physical laws operate under different conditions. A slight change in atmospheric chemistry can produce dramatically different outcomes. That's one of the recurring lessons of planetary science. Small differences often create enormous consequences. Temperature changes, pressure changes, cloud composition changes. Suddenly an entire planet takes on a completely different personality. Then there are lava worlds. These planets orbit so close to their stars that portions of their surfaces may exist as molten rock. When people hear the phrase lava planet, they often imagine something resembling Earth after an unfortunate encounter with a giant volcano. The reality is usually far more extreme. Some of these worlds possess temperatures capable of melting large portions of their surfaces continuously. Imagine oceans not of water, but of molten rock. Imagine glowing landscapes stretching toward horizons illuminated by nearby stars. Compared with TrES-2b, these worlds can appear astonishingly bright. Their temperatures produce visible emissions. Their surfaces radiate energy intensely. Where TrES-2b hides in darkness, lava planets often advertise their existence openly. The contrast is remarkable. Two hot worlds, two hostile environments, two entirely different appearances. Another fascinating category includes planets sometimes nicknamed eyeball worlds. These are typically tidally locked planets where one hemisphere constantly faces the star. The centre of the day side receives continuous illumination. The edges receive less. The night side remains permanently dark. Under certain conditions, liquid water might exist only in a circular region directly beneath the star. From space, the planet could resemble a giant eyeball, a bright central region surrounded by darker surroundings. Nature rarely concerns itself with whether its creations sound absurd. If physics allows something, the universe often tries it. And astronomy benefits as a result. Then we encounter worlds with bizarre weather systems. Some exoplanets may experience rainfall composed of materials unfamiliar on Earth. Not water, not snow, entirely different substances. In sufficiently hot environments, metals can vaporize. Minerals can enter atmospheric circulation. Clouds form from compounds that would seem completely out of place in terrestrial weather forecasts. Imagine opening a weather app and discovering a prediction involving silicate clouds. Fortunately, Earth remains somewhat more straightforward. At least most of the time, all these examples remind us of something important. Our solar system is not the standard model of planetary behaviour. For centuries it was the only example available. Naturally, people assumed it represented the norm. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The arrangement felt natural because it was familiar. Then exoplanets arrived and revealed an astonishing truth. The universe possesses far more imagination than we do. Planetary diversity appears almost limitless. Every discovery expands the menu. Every observation reveals new possibilities, and somewhere within that immense diversity sits TrES-2b. Not the hottest, not the largest, not the most massive, but certainly one of the darkest. Which brings us to an intriguing question. How common are worlds like it? If the universe contains billions of planets, surely TrES-2b cannot be unique, or can it? The answer is complicated. Astronomers suspect that extremely dark planets probably exist elsewhere. After all, the physical processes responsible for TrES-2b's darkness are not unique to one location. Atmospheric chemistry, temperature, radiation, cloud formation. These processes occur throughout the galaxy. Given enough planets, similar conditions should occasionally emerge. The challenge lies in detection. Dark planets are difficult to study precisely because they're dark. Imagine trying to conduct a census of invisible birds in a forest. The birds may be abundant, but if they're difficult to observe, determining their true numbers becomes challenging. Astronomers face a similar problem. Bright planets announce themselves more readily. Dark planets often hide. This introduces an observational bias. Scientists tend to discover certain kinds of worlds more easily than others. Large planets close to stars produce strong signals. Small planets far from stars produce weaker signals. Reflective planets reveal themselves differently than absorptive ones. As a result, the planets we know may not perfectly represent the planets that exist. The universe doesn't hand out balanced samples. Researchers must work carefully to account for those biases. Consequently, estimating the abundance of ultra-dark worlds remains difficult. Some may be hiding within existing data. Others may await discovery by future telescopes. Still others may possess atmospheric conditions even more extreme than those found on TrES-2b. The galaxy is large enough to accommodate remarkable possibilities. Very large. To appreciate just how large, consider this. The Milky Way alone contains roughly 100 billion stars, possibly more. Many of those stars possess planets. Some possess multiple planets. Recent estimates suggest that planets may actually outnumber stars. If true, our galaxy contains hundreds of billions of worlds. Hundreds of billions. It's a number so enormous that the human mind struggles to visualize it. Suppose you examine one planet every second. Without stopping, without sleeping, without taking breaks, it would still require thousands of years just to sample a tiny fraction of them. Against that backdrop, claiming that TrES-2b is unique becomes risky. Nature tends to repeat successful recipes. Somewhere else, another dark world may be circling another star. Perhaps darker, perhaps larger, perhaps stranger. We simply haven't found it yet. In fact, the history of astronomy suggests caution whenever declaring something the most extreme object in existence. Such titles rarely survive indefinitely. At various points, scientists believed they had discovered the hottest star. Then a hotter one appeared, the largest galaxy. Then a larger one emerged, the most distant object. Then observations pushed farther. Records fall regularly in astronomy. The universe is vast enough to make certainty dangerous. TrES-2b may remain one of the darkest known planets today. Tomorrow could bring a competitor. Future telescopes are especially likely to transform this field. The instruments currently being developed are astonishingly powerful. They will examine planetary atmospheres in greater detail than ever before, detect weaker signals, study smaller planets, observe more distant systems, and with every improvement comes the possibility of discovery, perhaps an even darker world. Perhaps a planet reflecting only a fraction of the already tiny amount reflected by TrES-2b. or perhaps something entirely unexpected? History suggests the latter is often the safer bet. Astronomers frequently set out looking for one thing and discover another. That's part of what makes the field so exciting. The universe continually provides surprises. Sometimes those surprises arrive as giant black planets. Sometimes they arrive as mirror-like worlds. Sometimes they arrive as environments nobody anticipated. Each discovery expands the boundaries of possibility, and each reminds us that our understanding remains incomplete. There's another reason ultra-dark worlds attract scientific interest. They serve as natural laboratories. Extreme environments help researchers test theories. A planet absorbing nearly all incoming starlight forces, atmospheric models into unusual territory. Scientists can compare predictions with observations, refine calculations, improve understanding. Even if such planets prove relatively rare, they remain valuable. Sometimes the most unusual examples teach the most important lessons. Biologists study rare organisms. Geologists study unusual formations. Physicists investigate extreme conditions. Astronomers do the same. The exceptions often reveal hidden rules. TrES-2b functions as one of those exceptions. A world whose darkness helps illuminate broader principles about atmospheres, radiation, and planetary behaviour. Which is wonderfully ironic when you think about it. A dark planet helping scientists see more clearly. Perhaps that's fitting. Some discoveries illuminate not through brightness, but through contrast. By standing apart from ordinary examples, they reveal things we might otherwise overlook. And as researchers continued studying TrES-2b, they eventually turned their attention toward another challenge. If planets can be this dark, how exactly do astronomers learn so much about them from hundreds of light years away? Suppose someone handed you a challenge. They place a bright spotlight on the opposite side of a city. Next to that spotlight sits a tiny insect. Your task is simple. Figure out the insect's size, its shape, its movement, its distance, and perhaps even what its wings are made of. There's just one problem. You're not allowed to walk closer. You're not allowed to touch it. You're not allowed to photograph it clearly. All you can do is study the light arriving from far away. Most people would immediately conclude that the challenge is impossible, and honestly, that would be a reasonable reaction. Yet astronomers perform something remarkably similar every day. The planets they study often lie hundreds, thousands, or even tens of thousands of light years away. Most cannot be photographed directly. Many are hidden in the glare of their stars. Some reflect almost no visible light at all. And still, scientists somehow determine their sizes, masses, temperatures, atmospheric compositions, orbital periods, wind patterns, and even hints about their weather. When people first learn this, they often assume there must be some secret trick involved, some extraordinary telescope capable of producing detailed planetary photographs, some hidden technology that transforms distant worlds into crystal-clear images. The truth is actually far more impressive. Astronomers accomplish these feats primarily through patience, physics, mathematics, and an extraordinary ability to extract information from tiny signals. In many ways, modern astronomy resembles detective work more than sightseeing. The universe leaves clues. Scientists follow them. TrES-2b offers a perfect example. Everything we've discussed so far, the darkness, the orbit, the temperatures, the atmospheric behaviour, comes from clues. No spacecraft has visited the planet. No probe has entered its atmosphere. No astronaut has seen it with their own eyes. Everything we know comes from light, or sometimes from the absence of light. That distinction turns out to be surprisingly important. The first major clue came through the transit method. We've touched on this before, but it's worth exploring in greater detail because it remains one of the most successful planet hunting techniques ever invented. Imagine staring at a distant star. For days, weeks, or months, the star maintains a fairly constant brightness. Then, very briefly, it dims. Not much, perhaps only a tiny fraction of a percent. Then the brightness returns to normal. Several days later, the same thing happens again, and again, and again. A pattern emerges. Something is repeatedly passing in front of the star. Something is blocking part of the starlight. The most likely explanation is a planet. This sounds simple enough, yet the precision involved is astonishing. Consider Earth's transit across the Sun as viewed from a distant location. The decrease in brightness would be incredibly small. Detecting such changes requires instruments capable of measuring light with extraordinary accuracy. Modern telescopes do exactly that. They monitor stars continuously, recording brightness levels, searching for tiny periodic dips, looking for patterns hidden within enormous amounts of data. When astronomers discovered TrES-2b, this method provided the first major breakthrough. The planet revealed itself not through reflected light but through blocked light. Every orbit produced a predictable dimming event. The star acted like a giant cosmic flashlight. The planet acted like an object moving through the beam, and the resulting shadow became detectable from hundreds of light years away. From those measurements alone, scientists could already estimate something important: size. The amount of dimming depends largely on how much of the star gets covered. A larger planet blocks more light. A smaller planet blocks less. Imagine placing different coins in front of a lamp. A large coin creates a bigger shadow. A small coin creates a smaller one. The same principle applies here. By measuring the depth of the transit, astronomers estimate planetary diameter. It's remarkable when you think about it. A tiny change in brightness reveals the size of a world no human will likely ever visit. But the transit method is only the beginning. Once a planet is discovered, astronomers immediately begin asking additional questions. How massive is it? What is it made of? How close is it to its star? What kind of atmosphere surrounds it? Answering those questions requires additional techniques. One of the most important is called the radial velocity method. The name sounds technical, but the underlying concept is surprisingly intuitive. People often imagine planets orbiting stars while stars remain perfectly stationary. Reality is more interesting. A planet exerts gravity on its star just as the star exerts gravity on the planet. The star is much more massive, so the effect is small, but it exists. Both objects actually orbit a shared centre of mass. As a result, the star wobbles slightly. Imagine two dancers holding hands. If one dancer is much larger, the smaller dancer appears to move around the larger one, yet the larger dancer moves too, just less dramatically. Stars and planets behave similarly. Astronomers detect these stellar wobbles by studying light. When a star moves toward Earth, its light shifts slightly. When it moves away, the shift reverses. These changes are tiny, extraordinarily tiny. Yet modern instruments can measure them. From those measurements, scientists estimate planetary mass. This means that without ever seeing the planet directly, astronomers can determine both size and mass. And once size and mass are known, another piece of information emerges: density. Density turns out to be incredibly useful. Imagine two planets of identical size. One possesses very low density, the other possesses high density. The low-density world might be a gas giant. The high-density world might be rocky. The planets look similar in diameter, yet their internal structures differ enormously. Density helps reveal the difference. For TrES-2b, these calculations confirm that the planet belonged to the hot Jupiter category, a giant gas world rather than a rocky Earth-like planet. Already, scientists had learned an astonishing amount from little more than starlight, yet they weren't finished, not even close. The next challenge involved understanding the atmosphere. At first glance, that sounds impossible. How can someone study the atmosphere of a planet hundreds of light years away? Surely atmospheric chemistry requires direct sampling, a probe, a spacecraft, some kind of physical interaction? Surprisingly, it doesn't. Again, light provides the answer. When starlight passes through a planetary atmosphere during a transit, certain wavelengths get absorbed more strongly than others. Different molecules leave distinctive signatures. Hydrogen absorbs light differently than sodium. Sodium behaves differently than water vapor. Water vapor behaves differently than methane. Each substance leaves fingerprints. Not literal fingerprints, of course. Spectral fingerprints. Patterns hidden within light. Astronomers spread starlight into its component colours using instruments called spectrographs. The resulting spectrum acts almost like a barcode. Tiny features reveal chemical information. By studying those features carefully, scientists infer atmospheric composition. Imagine hearing a musical chord. Even without seeing the instruments, an experienced musician might recognise a piano, a violin, and a trumpet contributing to the sound. Spectroscopy works similarly. Different molecules contribute distinctive signals. Astronomers learned to recognise them. This technique revolutionised exoplanet science. Suddenly planets stopped being mere points in a catalogue. They became places with atmospheres, places with chemistry, places with weather, places possessing unique environmental conditions, and in the case of TrES-2b, those observations gradually revealed an atmosphere unlike anything found in our solar system. But perhaps the most impressive achievement involved determining how dark the planet actually was. This required another layer of detective work. Scientists needed to measure reflected light. Remember, TrES-2b reflects less than 1% of incoming starlight. That signal is extraordinarily faint. Trying to measure it resembles trying to detect the brightness of a firefly sitting beside a stadium floodlight. The star dominates everything. The planet contributes almost nothing, yet almost nothing is still something. And astronomers became remarkably skilled at measuring it. One useful technique involves observing what happens when the planet passes behind its star. During this event, called a secondary eclipse, the planet disappears from view temporarily. Any light originating from the planet vanishes. Astronomers compare observations before, during, and after the eclipse. The differences reveal information about the planet's contribution. Think of it like listening to a duet. If one singer suddenly stops singing, you can identify which notes belong to that performer. Similarly, when the planet disappears behind the star, scientists isolate its signal. The resulting measurements help confirm TrES-2b's extraordinary darkness. Without secondary eclipse observations, determining the planet's reflectivity would have been far more difficult. This approach demonstrates something fascinating about modern astronomy. Scientists rarely measure a single property directly. Instead, they combine multiple observations. Each observation contributes one piece of the puzzle: size from transits, mass from stellar wobble, atmospheric clues from spectroscopy, reflectivity from secondary eclipses, temperature from infrared measurements. Eventually a coherent picture emerges. The process resembles assembling a giant cosmic jigsaw puzzle without ever seeing the completed image. Each piece matters, each clue contributes, and over time, a distant world takes shape. The role of space telescopes deserves special attention here. Many of the most important exoplanet discoveries would be impossible from Earth's surface alone. Our atmosphere, wonderful as it is for supporting life, complicates astronomical observations. Air moves, temperatures fluctuate, water vapor absorbs certain wavelengths. The atmosphere introduces noise. Space telescopes avoid many of these problems. Above Earth's atmosphere, observations become cleaner, more stable, more precise. The Kepler Space Telescope transformed exoplanet science for precisely this reason. It stared continuously at thousands of stars, searching for transits, recording tiny brightness changes. Its observations contributed enormously to our understanding of planets like TrES-2b, and newer observatories continue pushing the field forward. Each generation of telescopes sees farther, measures more accurately, reveals additional details. What seems impossible today often becomes routine tomorrow. That's been the pattern throughout astronomical history. Another fascinating aspect of this work involves computer modelling. Observations alone rarely provide complete answers. Scientists build models to test ideas. Suppose measurements suggest a particular temperature. Researchers ask what atmospheric conditions could produce that temperature. Suppose observations indicate unusual reflectivity. Models explore possible explanations. Different scenarios compete, predictions emerge. New observations determine which predictions succeed. The process resembles an ongoing conversation between theory and evidence. Neither works alone. Together they gradually improve understanding. TrES-2b benefited enormously from this approach. The darkness posed a puzzle. Models helped identify possible explanations. Observations tested those explanations. Over time, the picture became clearer, not perfect. Science rarely achieves perfection, but clearer. And that's often enough. Perhaps the most remarkable thing about all this is how normal it has become. A few decades ago, discovering planets around other stars was revolutionary. Today, astronomers routinely discuss atmospheric chemistry on worlds hundreds of light years away. They estimate temperatures, measure winds, study clouds, determine orbital properties, all without leaving Earth. The accomplishment is extraordinary, and it continues improving every year. Somewhere among the countless stars of the Milky Way, billions of planets likely remain undiscovered. Many will challenge our assumptions. Some may be stranger than TrES-2b. Others may resemble Earth more closely. Each will leave clues hidden in light. And astronomers will continue learning how to read those clues. Because in the end, astronomy is fundamentally about information. Light carries stories. Every photon arriving at a telescope contains a fragment of a message. Scientists decode those messages, piece them together, and transform distant worlds from invisible mysteries into places we can begin to understand. TrES-2b is one of those places, a giant dark planet orbiting a distant star, a world revealed through patience, mathematics, and remarkable ingenuity. And thanks to those methods, astronomers gained far more than a simple discovery. They gained insight into how atmospheres behave under extreme conditions. They gained clues about planetary evolution. They gained a deeper understanding of why some worlds shine while others absorb nearly everything. Beyond its record-setting darkness, what has TrES-2b actually taught us about planets themselves? Imagine for a moment that every planet in the universe wore a mask. Not a literal mask, of course. A scientific one. A layer that hides what lies beneath. A layer that controls what outsiders see. A layer that determines whether a world appears bright or dark, hot or cool, calm or chaotic. That mask is the atmosphere. And if astronomers have learned anything from studying exoplanets over the last few decades, it's that atmospheres can completely transform a planet's identity. Two planets might have similar sizes, similar masses, similar distances from their stars, yet if their atmospheres differ, the worlds themselves can become almost unrecognizable compared to one another. One may reflect sunlight brilliantly, another may absorb nearly everything, one may trap heat efficiently, another may allow it to escape. One may possess thick clouds, another may have skies nearly free of them. Atmospheres shape planetary character in ways that are difficult to overstate, and few worlds demonstrate this more dramatically than TrES-2b. At first glance, the planet's most famous feature seems straightforward. It's dark, extraordinarily dark, one of the darkest planets ever discovered. That's the headline. That's the fact that appears in articles and documentaries. Yet from a scientific perspective, the darkness itself is only the beginning. The truly important question is why? Why does the atmosphere behave this way? What processes create such remarkable absorption? And perhaps most importantly, what does this tell us about atmospheres elsewhere in the universe? because astronomers are not really interested in TrES-2b simply because it is unusual. Scientists rarely study things merely because they are strange. They study them because strange objects often reveal broader truths. A single unusual example can expose weaknesses in existing theories. It can reveal missing pieces of knowledge. It can uncover processes that operate elsewhere but are easier to recognize under extreme conditions. In many fields of science, the exceptions become the most valuable teachers. TrES-2b is one of those teachers. The planet forces researchers to confront a simple reality. Atmospheres are far more complex than we once imagined. For most of human history, atmospheric science was limited to a sample size of 1, Earth. Everything we knew about atmospheres came from living inside one. That creates certain assumptions. We become accustomed to blue skies, water clouds, rain, snow, winds driven by familiar temperature differences. Even after astronomers began studying Venus, Mars, Jupiter, and the other planets in our solar system, the sample size remained relatively small, useful, interesting, but still limited. Then exoplanets arrived. Suddenly the universe provided thousands of new examples, thousands of atmospheric laboratories operating under different conditions, different temperatures, different gravities, different stars, different chemical environments, and almost immediately those atmospheres began surprising us. Some were hotter than expected, some cooler, some puffier, some denser. Some appeared cloudy, others appeared strangely clear. Every new discovery expanded the range of possibilities. TrES-2b expanded it dramatically. Before worlds like TrES-2b were discovered, many assumptions about atmospheric reflectivity seemed fairly reasonable. After all, giant planets in our solar system tend to be somewhat reflective. Jupiter reflects a respectable amount of sunlight. Saturn does as well. Clouds scatter incoming radiation. Atmospheres brighten the planet. The pattern feels familiar. Then, TrES-2b arrived and seemed determined to challenge that expectation. Its atmosphere demonstrated that giant planets can become astonishingly effective absorbers. This forced scientists to reconsider how atmospheric chemistry operates under extreme conditions. One of the major lessons involves the importance of temperature. Temperature influences nearly everything in an atmosphere. Cloud formation, chemical reactions, molecular stability, energy transport, the behavior of gases. Change the temperature enough, and the atmosphere becomes an entirely different system. Imagine taking Earth's atmosphere and gradually heating it. Cloud behavior changes, weather changes, chemistry changes. Continue heating, and eventually the atmosphere enters regimes that no longer resemble anything familiar. TrES-2b lives permanently in one of those regimes. Its temperatures are so high that atmospheric processes operate under conditions rarely encountered elsewhere. This realization helped researchers appreciate something important. There is no such thing as a typical atmosphere. Atmospheres are products of their environments. Move a planet closer to its star and everything changes. Move it farther away and everything changes again. Change the star itself and new possibilities emerge. The diversity becomes enormous. Another lesson concerns clouds. Clouds may seem simple because we encounter them every day. Yet from a planetary perspective, clouds are incredibly influential. They regulate temperatures, reflect light, transport energy, shape climate. Even small changes in cloud behavior can transform an entire world. On Earth, clouds contribute significantly to our planet's brightness. Without them, Earth's appearance from space would be very different. Venus provides an even stronger example. Its thick cloud layers reflect enormous amounts of sunlight. Those clouds help make Venus one of the brightest objects in our sky. TrES-2b illustrates the opposite possibility. Its atmospheric conditions appear hostile to the kinds of reflective cloud systems that might otherwise brighten the planet. As a result, incoming starlight encounters fewer opportunities to escape. The atmosphere becomes darker. The planet absorbs more energy. Everything changes. This lesson extends far beyond a single exoplanet. It reminds scientists that cloud formation cannot be treated as a minor detail. Clouds are often among the most important factors determining how a planet appears. Another important lesson involves atmospheric circulation. Earlier we discussed the powerful heating experienced by TrES-2b. That heating creates enormous energy imbalances. One side receives relentless stellar radiation. The atmosphere responds by moving heat. This process revealed something fascinating about planetary weather. Atmospheres can transport staggering amounts of energy, far more than most people realize. On Earth, atmospheric circulation redistributes heat from equatorial regions toward the poles. Without that circulation, climates would become far more extreme. TrES-2b operates on the same basic principle. The difference is scale. Everything becomes larger, hotter, more intense. The atmosphere works continuously to redistribute absorbed energy. By studying these processes, astronomers gain insights into how atmospheric circulation functions under conditions impossible to recreate on Earth. It's like having access to a natural laboratory, larger than any experiment humans could ever build. And because nature has been running the experiment for millions or billions of years, the results become especially valuable. Another fascinating lesson involves absorption itself. Prior to studying worlds like TrES-2b, many atmospheric models focused heavily on reflection. Reflection is easy to notice. Bright planets attract attention. Reflective clouds stand out. Absorption often receives less attention because it is less obvious visually. TrES-2b changed that perspective. Its darkness demonstrated how powerful absorption can become. The atmosphere effectively acts as an energy collection system. Incoming radiation enters, most remains, temperatures rise, atmospheric behavior changes. The consequences ripple throughout the entire planet. Researchers studying atmospheric evolution now pay much closer attention to these processes, because what happens to absorbed energy matters enormously. It influences weather, climate, chemistry, even long-term planetary development. In a sense, TrES-2b became a reminder that darkness itself can be scientifically informative. The absence of reflected light tells a story, sometimes a very important one. The planet also taught scientists something about observational assumptions. Throughout the history of astronomy, researchers have repeatedly encountered the same lesson. The universe is under no obligation to conform to human expectations. Again and again, observations reveal possibilities nobody predicted. TrES-2b provided another example. Many atmospheric models anticipated certain behaviors. The planet revealed others. The discrepancy encouraged refinement, improved calculations, better understanding. That's one of the healthiest processes in science. Unexpected discoveries force theories to evolve. Without surprises, progress becomes difficult. TrES-2b supplied a very useful surprise. Another area where the planet proved valuable involves atmospheric chemistry. Under extreme temperatures, molecules behave differently. Some compounds remain stable, others break apart. Still others form unexpectedly. The chemistry of hot exoplanets became a major field of study, partly because worlds like TrES-2b demonstrated how much remained unknown. Researchers began asking new questions. Which molecules dominate under such conditions? How do they interact with radiation? What signatures should astronomers expect? How do these chemicals influence planetary appearance? The answers continue emerging today. Every new observation adds detail. Every improved model refines understanding, and every refinement helps scientists interpret other planets more accurately. Because that's the broader goal. Astronomers aren't studying TrES-2b in isolation. They're using it to understand planetary atmospheres as a whole. Every lesson learned there can be applied elsewhere. That's especially important because the future of exoplanet science increasingly focuses on atmospheres. Finding planets is no longer the primary challenge. Thousands have already been discovered. Now the challenge involves understanding them. What are they like? What processes shape them? How do atmospheres evolve? Which worlds resemble one another? Which stand apart? Atmospheric studies provide many of the answers. TrES-2b occupies an important place within that effort, not because it represents the average planet, but because it represents an extreme one. Extreme examples often clarify general principles. Consider athletics. Studying the fastest runners reveals information about human physiology. Studying the deepest ocean trenches reveals information about geology. Studying the hottest stars reveals information about stellar physics. Likewise, studying one of the darkest planets reveals information about atmospheric behavior. The exception illuminates the rule. There's also a philosophical lesson hidden within all this. For centuries, humans tended to think of planets as relatively simple places. Large rocks, large gas spheres, worlds that differed mainly in size and distance. Exoplanets changed that perception completely. Today we understand that planets possess personalities. Not conscious personalities, of course. Physical personalities. Distinct identities shaped by chemistry, temperature, gravity, radiation, and history. TrES-2b possesses one such identity: dark, hot, absorptive, extreme, a world shaped by its relationship with a nearby star, and through that identity it teaches us something broader. Planetary atmospheres are not decorative features, they are fundamental components of planetary existence. They determine how worlds look, how they behave, how they evolve. Sometimes they even determine whether a planet becomes memorable. Without its atmosphere, TrES-2b would not be famous. Without its atmosphere, it would simply be another gas giant orbiting another distant star. The atmosphere created the darkness. The darkness created the mystery. The mystery created the scientific interest. In many ways, the entire story begins there. And once scientists began appreciating just how much atmospheres can vary, a larger realization emerged. If one planet can become this dark, and another can become brilliantly reflective, and another can possess molten surfaces, and another can host exotic clouds, then perhaps our assumptions about what constitutes a normal planet need to be reconsidered entirely. Because the more worlds we discover, the stranger the universe appears, and TrES-2b serves as a perfect reminder of that reality. A reminder that atmospheres can transform worlds in extraordinary ways. For most of human history, the universe seemed surprisingly orderly. The sun occupied the center of our daily experience. The moon circled Earth. The planets moved across the sky in predictable patterns. Stars appeared fixed, permanent, reliable. Even after scientific understanding improved, people still tended to imagine the cosmos as a place governed by familiar rules. Planets would probably resemble the ones in our own solar system. Stars would probably possess planetary families arranged in roughly similar ways. The overall structure might vary, but not dramatically. At least that was the expectation. Then astronomers began discovering exoplanets, and little by little, those expectations started falling apart. The process didn't happen all at once. It happened discovery by discovery. One strange world appeared, then another, then another. At first, researchers assumed the unusual examples were exceptions, rare oddities, statistical curiosities, but as the number of known exoplanets climbed into the thousands, a different picture emerged. The strange worlds were not exceptions. They were part of the rule. The universe turned out to be far more creative than anyone had anticipated, and TrES-2b sits comfortably within that growing collection of surprises. Not because it is the largest planet ever discovered, not because it is the hottest, not because it possesses the most unusual orbit. Its significance comes from something deeper. TrES-2b reminds us that reality often exceeds imagination. When people invent fictional worlds, they usually rely on experiences they already understand. A writer creating an alien planet might start with a desert, or an ocean, or a frozen landscape, then add unusual details, perhaps two suns, perhaps giant storms, perhaps strange colours in the sky. Human imagination tends to modify familiar concepts. Nature doesn't have that limitation. Nature begins with physics and follows the results wherever they lead. Sometimes the destination is a giant dark world, orbiting so close to its star that a year lasts less than 3 Earth days. No committee designed TrES-2b. No artist sketched it into existence. No storyteller invented it. The planet emerged naturally from the same physical laws operating throughout the universe. And that's what makes it so fascinating, because if physics can create TrES-2b, what else can it create? That question sits at the heart of modern planetary science. Every unusual planet becomes a clue. Every strange atmosphere becomes a lesson. Every unexpected discovery reveals something about how planets form and evolve. TrES-2b contributes significantly to that effort. To understand why, we need to step back and consider one of astronomy's biggest questions. How do planets form in the first place? Today, the basic outline is fairly well understood. Stars form from collapsing clouds of gas and dust. As a young star emerges, material remains orbiting around it. This material forms a rotating disk. Within that disk, tiny particles collide. Some stick together. Those larger pieces collide with other pieces. Gradually, small objects become larger objects. Larger objects become planetary embryos. Planetary embryos become planets. At least that's the simplified version. Reality is considerably messier. Disks evolve, objects migrate, collisions occur, gravitational interactions reshape entire systems. The process resembles construction, demolition, and traffic congestion all happening simultaneously. And because every planetary system begins with slightly different conditions, the final results vary enormously. This is one reason exoplanets became so important. Before exoplanets, astronomers had only one completed example of planetary formation, our solar system. That's like trying to understand human biology after meeting a single person. You can learn a lot. But there are limits. Exoplanets dramatically increase the sample size. Suddenly scientists could compare thousands of planetary systems. Patterns emerged. Unexpected patterns. One of the first major surprises involved hot Jupiters, planets like TrES-2b. Before their discovery, many researchers assumed giant gas planets would generally remain far from their stars. That expectation came directly from our own solar system. Jupiter resides far from the Sun. Saturn resides even farther. The arrangement seemed logical. Large gas giants form in colder regions where abundant material exists. Simple, reasonable, apparently incomplete. When hot Jupiters started appearing, planetary formation theories faced a challenge. How did giant planets end up so close to their stars? The environment near a young star seems unfavourable for forming a massive gas giant directly. Temperatures become extreme. Material behaves differently. The situation appears complicated. Scientists eventually developed an explanation that is now widely accepted. Many hot Jupiters probably formed farther away from their stars and migrated inward later. Migration sounds simple. In reality, it is one of the most dramatic events a planet can experience. Imagine Jupiter suddenly deciding to move toward the Sun. Its journey would reshape the entire solar system. Orbits would change. Gravitational interactions would occur. Smaller worlds might be displaced. Everything would become chaotic. Similar processes likely occurred in many planetary systems. A giant planet forms. Interactions begin. The orbit evolves. Gradually the planet spirals inward. Eventually it settles into a tight orbit close to its star. The result is a hot Jupiter, a world like TrES-2b. This realization changed planetary science profoundly. Planets were no longer viewed as stationary products of formation. They became travelers, migrators, dynamic participants in evolving systems. Their present locations do not necessarily reveal where they originated. That's an important lesson. When astronomers observe TrES-2b today, they are seeing the final chapter of a much longer story. The planet likely wasn't born where it currently resides. Its history probably involved movement, change, transformation. The darkness we observe today may be linked indirectly to events that occurred billions of years ago. Another important lesson concerns planetary diversity. Before exoplanets, it was tempting to assume that most planetary systems resembled ours. After all, our solar system was the only example available. Now we know better. Some systems contain giant planets extremely close to their stars. Some contain tightly packed groups of worlds. Some contain planets orbiting multiple stars. Others contain architectures unlike anything found in our cosmic neighborhood. Planetary systems are not manufactured according to a universal template. Nature experiments constantly. The results vary. TrES-2b serves as one example among many. Its existence reinforces a simple but powerful idea. There is no such thing as a standard planetary system. There are only planetary systems. Each one follows its own history, its own sequence of events, its own evolutionary path. The implications become even more fascinating when we think about habitability. Whenever people hear about exoplanets, one question tends to appear quickly. Could life exist there? In the case of TrES-2b, the answer is almost certainly no. The temperatures are far too extreme, the environment is far too hostile, the planet itself is a gas giant. Everything about it points toward conditions incompatible with life as we know it. Yet TrES-2b still contributes to the search for habitable worlds. That may sound strange. How can an uninhabitable planet help scientists search for habitable ones? The answer involves understanding possibilities. To identify Earth-like worlds, astronomers must first understand non-Earth-like worlds. Every discovery expands the catalogue. Every unusual atmosphere improves planetary models. Every strange system teaches researchers what nature is capable of producing. Knowledge accumulates. The search becomes more effective. In that sense, TrES-2b acts like a teacher once again. Its darkness reveals atmospheric processes. Its orbit reveals migration history. Its existence reveals planetary diversity. Each lesson contributes to broader scientific understanding. Another remarkable consequence of exoplanet discoveries involves human perspective. For thousands of years, people naturally viewed Earth as special, not necessarily because it was unique, but because it was familiar. It was home, the center of experience, the place where every story unfolded. Then astronomy gradually expanded our horizons. Earth became one planet among several. The Sun became one star among billions. The Milky Way became one galaxy among countless others. Exoplanets continued this trend. Now Earth is not merely one planet among several. It is one planet among potentially hundreds of billions within our galaxy alone. That realization changes how we think. Not always consciously, but profoundly. The universe becomes larger. Possibility expands. Wonder increases. TrES-2b contributes to that expansion. Because every strange planet reminds us that reality extends far beyond our everyday experience. No human standing beneath a night sky would naturally imagine a world darker than almost anything else known. Yet such worlds exist. No human observing the planets of our solar system would automatically predict hot Jupiters. Yet they exist. No human looking at Earth would easily imagine many of the environments now known among exoplanets. Yet they exist too. Reality continues outperforming expectation. Perhaps that's the deepest lesson of all. Science is not merely a collection of facts. It is a process that continually reveals how incomplete our assumptions can be. Every discovery expands the boundaries of the possible. Every observation reminds us that nature is under no obligation to behave according to human intuition. TrES-2b embodies that principle beautifully. At first glance, the planet sounds impossible. A giant dark world orbiting beside a blazing star. A place where extraordinary heat coexists with extraordinary darkness. A world that absorbs nearly everything. Yet there it is. Not hypothetical, not speculative. Real. Orbiting a real star hundreds of light years away. Continuing its journey regardless of whether anyone happens to be watching. And if one such world exists, countless others almost certainly await discovery. Some may be darker, some brighter, some stranger, some more familiar. Future telescopes will find them. Future astronomers will study them. Future generations will add new entries to the growing catalogue of planetary possibilities. The process has only just begun. That's an astonishing thought when you consider how recently exoplanet science emerged. The first confirmed discoveries occurred within living memory. Many of the people who helped establish the field are still alive today. In astronomical terms, we're witnessing the opening moments of exploration. The first pages of a much longer story. TrES-2b represents one paragraph within that story. A memorable paragraph, certainly, but still part of something much larger. A broader effort to understand how planets form, how atmospheres evolve, how solar systems develop, and ultimately how common different kinds of worlds may be throughout the universe. Because every time astronomers uncover another unusual planet, the same realization returns. The universe is not becoming less mysterious, it's becoming more interesting. After all the measurements, discoveries, atmospheric models, and scientific lessons, what does it actually mean that a giant dark world exists so far from home? What should we take away from a planet that spends its entire existence orbiting in perpetual darkness and relentless heat? Somewhere in the constellation Draco, hundreds of light years from Earth, a planet continues its endless journey around a distant star. Right now, at this very moment, while cities glow beneath streetlights, while trains move through tunnels, while people finish late dinners, read books, watch television, or prepare for sleep. While countless ordinary moments unfold across our world, TrES-2b is still there, orbiting, absorbing starlight, racing through another impossibly short year, completely unaware that anyone has ever given it a name. That thought has always been one of the most fascinating aspects of astronomy. The universe does not perform for us. The stars are not putting on a show. The planets are not trying to be discovered. Everything simply exists, following the laws of physics, obeying gravity, responding to energy and time. Long before human beings learned to build telescopes, TrES-2b was already circling its star. Long before the first cities appeared on Earth, long before written language, long before agriculture, long before our species had any idea what a planet actually was, that distant world was already there, dark, hot, silent, moving through space according to rules that would eventually be understood billions of years later by creatures living around another star. There is something wonderfully humbling about that. Throughout this journey we've talked about measurements, atmospheres, temperatures, orbital periods, reflectivity, cloud formation, planetary migration. The science matters. It always matters. Science is the reason we know TrES-2b exists at all. Without careful observations, without mathematics, without telescopes and generations of researchers, the planet would remain completely unknown to us. And yet, after all the numbers are finished, after all the calculations have been completed, something else remains. Perspective. Because TrES-2b is not important merely because it is dark. If darkness alone were enough, there would be little reason to remember it. The planet matters because of what it represents. A reminder that reality is larger than familiarity. For most of human history, the planets we knew were the planets of our own solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Those worlds shaped our expectations. Understandably so, they were the only examples available. If someone had described TrES-2b 1,000 years ago, the story would have sounded absurd. A giant black world orbiting extremely close to a star, a planet so dark that it reflects less than 1% of incoming light. A world where extraordinary heat and extraordinary darkness exist together. The description feels almost contradictory, and yet reality doesn't care whether something sounds believable. Reality simply is. Again and again, astronomy teaches the same lesson. The universe is not limited by human intuition. What seems impossible often turns out to be merely unfamiliar. What sounds strange today may become completely normal tomorrow. History is full of examples. There was a time when galaxies beyond the Milky Way sounded improbable. Then we discovered them. There was a time when black holes seemed almost ridiculous. Then evidence accumulated. There was a time when planets around other stars existed only in speculation. Today we know of thousands. Each generation expands the boundaries of the known universe. Each generation encounters discoveries that would have astonished the one before it. TrES-2b belongs to that tradition, not because it rewrites all of physics, not because it breaks scientific laws, quite the opposite. The planet follows those laws perfectly. Its darkness emerges from physics, its atmosphere emerges from physics, its temperature emerges from physics, its orbit emerges from physics. Everything about the world makes sense once enough information is gathered, and perhaps that's what makes astronomy so satisfying. The universe is filled with surprises, but those surprises are understandable. The mysteries are real. The explanations are real too. Sometimes they simply take time to uncover. It's worth pausing for a moment and thinking about how remarkable that process truly is. A species living on a small planet around an ordinary star somehow learned to study a giant dark world hundreds of light years away. No spacecraft travelled there. No astronaut visited. No sample was collected. Everything came from light. Tiny changes in brightness. Faint signals crossing unimaginable distances. Patterns hidden within data. Human curiosity transformed those clues into understanding. That achievement is extraordinary. We often become accustomed to scientific accomplishments because we hear about them regularly. New discoveries arrive, new headlines appear, new worlds enter the catalogue. It's easy to forget how remarkable the process actually is. Imagine explaining exoplanet science to someone living 500 years ago. You tell them that people can estimate the temperature of a planet they cannot see directly. You tell them they can study atmospheric chemistry from across interstellar space. You explain that a giant world has been identified primarily through tiny changes in starlight. The entire conversation would sound like magic, and yet it isn't magic. It's observation, patience, technology, mathematics. Generations of people asking questions and refusing to stop looking for answers. TrES-2b is one result of that effort. One world among thousands, one discovery among many, and still memorable. Perhaps because darkness carries a special fascination. Human beings have always been interested in darkness. We fear it sometimes, seek it out at other times. We build lights to push it away, then travel great distances to experience it again beneath star-filled skies. Darkness occupies a curious place in human imagination, part mystery, part comfort, part unknown. TrES. 2b takes that fascination and stretches it across astronomical distances. A dark world. Not metaphorically, not symbolically, physically, measurably, scientifically. One of the darkest planets ever discovered. And yet even there, darkness is not absolute. That's another lesson worth remembering. Throughout this story, we've repeatedly encountered the same idea. The planet is dark, but not invisible. The atmosphere absorbs light, but not all light. The world seems hidden, yet it can still be studied. Nature rarely deals in absolutes. The closer we look, the more nuance we find. Even the darkest known planets still emit energy. Even apparently empty space contains structure. Even silence contains information if one listens carefully enough. Astronomy rewards that kind of attention, the willingness to notice small things, tiny changes, subtle clues, faint signals. Entire worlds reveal themselves through details that would be easy to overlook. Perhaps that's one reason astronomy feels surprisingly peaceful, at least compared with many other sciences. The discipline encourages patience. Stars do not hurry, planets do not hurry, galaxies certainly do not hurry. Everything unfolds on timescales far larger than human schedules. The universe remains perfectly content to wait, and in a world that often feels rushed, there is something comforting about that. TrES-2b has been orbiting its star for an unimaginably long time. It will likely continue doing so long after every person alive today is gone. The planet doesn't care about deadlines. It doesn't care about trends. It doesn't care about news cycles. It simply follows its path. Again, and again, and again. A year every couple of days, an orbit completed, another begins, the cycle repeats. Endlessly from a human perspective. That scale can feel overwhelming at first, then strangely calming. The universe is vast, older than human civilization, older than humanity itself, yet somehow we're capable of understanding pieces of it. Not all of it. Probably never all of it, but pieces. Enough to know that worlds like TrES-2b exist. Enough to know that the galaxy contains extraordinary diversity. Enough to know that our cosmic neighbourhood is far stranger than we once imagined. And perhaps that's the best note on which to leave this story. Not certainty, curiosity. Because TrES-2b is not the end of anything. It is one example, one discovery, one chapter in a much larger exploration. Somewhere beyond it are other planets, other atmospheres, other mysteries. Some may be brighter, some darker, some hotter, some colder, some stranger than anything we've discussed tonight. Future telescopes will find them. Future astronomers will study them. Future discoveries will once again expand the boundaries of possibility. The story continues. It always does. For now, though, our attention returns home, back to Earth, back to the room around you, back to whatever time of night it happens to be where you are. Perhaps the lights are already off. Perhaps you're looking toward a window. Perhaps you're listening with your eyes closed. Wherever you happen to be, take a moment to remember something remarkable. Above your world hangs a sky filled with stars. Around many of those stars orbit planets. Around some of those planets are atmospheres unlike anything we know. And around one distant star, hundreds of light years away, a giant dark world continues racing through space, absorbing starlight, holding its secrets, circling endlessly beneath a sky that never changes. A quiet planet lost in eternal night. And while it continues that distant journey, there will always be another question waiting beyond it. Another mystery, another world, another reason to look upward and wonder what else might be out there, hidden among the countless lights scattered across the darkness.